our colleague actually, our dear colleague Fatima Amroué gave me the opportunity to hijack the meeting and say a few words on behalf of the math department actually. So I am the chairperson of the math department, and I have to tell you that, for instance, in our department, we do have a flyer, and it goes along like promoting the importance of, mastering the language, that mathematics is about the common languages of all sciences. For the students, actually, so we do that, we try to attract many students actually in our major. But for students, we do not have this, belief. So we actually have special courses for them. So we have mathematical for life sciences, statistics for health sciences. And well, I think this is fun, but actually if you want to go further, I think you do really need to a very heavy background, very good background in mathematics to be able to actually later on to do major contribution in other fields, in particular in health sciences. And I think that this meeting now, this is the core. I mean, this is at a common intersection of the mission of our department, but also of the mission of this meeting, that you can, in case you actually want to do like very crucial contribution to a field important like biomedical issues and stuff like that. So with a mathematical approach, you really need to be a mathematician. So I'm glad that this meeting is showing a different way for our majors as well, with clear application, important application of how to actually use mathematics to modelize the growth of tumors or the kind of phenomenon that we will hear in the talk of Nader. So for this reason, I'm very thankful for our dear colleague Fatima Amroué, who did an amazing job into putting all of this meeting together and coming up with a great army of speakers who are really showcasing great impact of mathematics in the field of in biomedical issues and the field of health sciences. So thank you very much, Fatima, for doing this amazing job. I'm going to introduce the first speaker of this morning. So this is Nader El-Khatib from the Lebanese American University, who will be talking about the mathematical modeling of atherosclerosis. Nader,
okay.
So, okay. So, again, so Professor Vitaly Volpert, a senior researcher at CNRS, and he's also the head of biomathematical modeling team in RUDN University in Russia. He's also the chief editor of the journal Mathematical Modeling of Natural Phenomena. Thank you for being with us this morning. And he will be talking about mathematical modeling of respiratory viral infections. Please, the floor is yours.
Yes, thank you very much for this introduction and also for the invitation to this workshop, the opportunity to present our recent works. So indeed, I will talk about what we recently did on mathematical modeling of respiratory viral infections. Of course, we are all aware about these infections, especially now. But in fact, first viral infections appeared many years ago, thousands of years ago, when first agricultural communities were formed. And since that, these epidemics of viral infection like accompany the whole human history. And of course, we are all very much concerned by this last and in fact ongoing COVID-19 pandemic. So what I will present today is, after a short biological introduction, I will talk basically about two questions. The first one is infection spreading in cell cultures or cell tissues, and we will talk, we'll discuss some how to characterize this infection spreading, in particular with the spreading speed, with viral load, and some other questions. And the second part of this presentation, related of course to the first one, will be about mucus motion in human airways during respiratory viral infections and how this can cause airway obstruction. This was also, of course, very important and largely observed for COVID-19 patients. So let us start with this short biological introduction. So what we should know about viruses: these are small particles Viruses cannot reproduce by themselves. They need host cells. So this is shown schematically in the slide. Virus penetrates the host cell. It liberates its genetic material, DNA or RNA. This genetic material integrates the nucleus of the cell. Then it is copied by like new RNA or DNA molecules, and then a new viral particle is formed, and it leaves the cell into the extracellular space. Of course, this is very simplified and schematic representation. At the same time, our body reacts to the viral infection, and this is what is called immune response. This is a very complex multi-stage process. It begins with the innate immune response mediated by the cells of innate immune response, such as macrophages or dendritic cells. This they are called also antigen-presenting cells because they integrate some part of the antigen, and with this part of the antigen on the receptors, they activate lymphocytes, T lymphocytes, and then after several steps of the development, these T lymphocytes become cytotoxic T lymphocytes. They are also called CD8+, or other type of lymphocytes, helper lymphocytes, CD4+. These helper lymphocytes, they also initiate B lymphocytes, and B lymphocytes produce antibodies. Then effector T lymphocytes eliminate infected cells, and antibodies neutralize viral particles. Of course, this is very shortly and very schematically how our immune response works. And of course, there are many experimental and clinical studies about viral infections. Here again, very shortly about some types of experiments. One of them in particular is called multiplicity of infections, also plaque assays, and I will return to that later. These are very useful and interesting experiments characterizing these viral infections. You see, this is, for example, the view from above. This is a petri dish with blue is cell culture. Then in the cell culture, they introduce a solution with viruses. These viruses penetrate cells, they begin to multiply, they expand, being transmitted from infected cells to the neighboring cells. And after some time, you see these white plaques. These are infected cells. They die after some time. This is why we see them is this white areas. So I will return to this later. It's very interesting, very important. And what is also we can see here that this can be different for different, in particular, variants of this SARS-CoV-2 infection. Again, I will return to this question later. Not only cell cultures, but also tissues, ex vivo, in vivo. So the huge domain of research and a lot of data related to that for different virus types. So I will begin with mathematical modeling of this infection progression in the human organism, considering cell culture with a very simple mathematical model shown here, 3 ordinary differential equations for U uninfected cells, W infected cells, V virus for their concentrations. In the first equation, there are 3 terms. The first one, the influx of uninfected cells. The last one, the death of uninfected cells. In many cases, we can neglect the first and the last terms because of different time scales. What is very important here, of course, how these uninfected cells are infected by virus. This is the second term. It is often considered is, well, in this macroscopic modeling, is this kind of a mass action law, the product of these 2 concentrations, U uninfected cells, V virus. The same term appears in the second equation. This is how, this is sign plus, this is how the infected cells appear. And the last term in this equation is death of infected cells. Not only the, say, natural death, but also death induced by infection. And the last equation is the equation for the virus concentration. Virus is produced by infected cells, is the first term on the right-hand side, and then virus can also die. And there are some other details like time delay and so on. We will not discuss it now. And then we have the simple model, and we do, for example, it can be studied analytically or numerically. And for example, you see here at the right an example of numerical simulations. It's normalized concentrations. Keep in mind here to understand how it is happening. The red curve is the concentration of uninfected cells. It decreases from some initial concentration. It decreases. Here, the concentration of infected cells, it's I believe it should be, well, okay, W, it's a blue curve. Blue curve is concentration of infected cells. In the beginning it is 0, then it grows, reaches its maximum, and then goes down. And then a little bit later, the concentration of virus, this green curve, also grows, then also decreases. So this is a very clear understanding on what is happening when viral infection develops in the human organism. We will start now build more complete and more complex model. So the next step, we introduced in the model the space variable, because both for cultures or tissues or human organism, infection does not develop everywhere at the same time. It spreads in space. So we have the same equations, except that in the last equation, we add this diffusion term. So virus can diffuse in the culture or in the tissue. Of course, it's quite complex because it is highly heterogeneous medium, and there are different mechanisms of virus transmission. It can be either direct cell-to-cell transmission, or virus can go to the extracellular space and diffuse there. But in this macroscopic description, we consider it as a diffusion term. And also here in this slide, you see this time delay in virus replication in the infected cells, which, by the way, is another notation, but it's not important. And then we study this model where there are different approaches like analytical or numerical. Here again, it is an example of numerical simulations here, and we see how this infection spreads in space now. So this is a snapshot. It's instantaneous for a fixed time. We have the same three concentrations, this blue curve for uninfected cells, green curve for infected cells, like a spike here, and this red or brown curve for the virus. And all the structure moves together as shown here, here from the left to the right with certain speed. And in fact, solutions like that in mathematics, we call them traveling wave solutions. And then we can study different mathematical questions or modeling questions, in particular, for example, from the mathematical point of view, the question of existence of such solutions. Of course, in today's presentation, I will not discuss these mathematical questions. It would be much longer. But what I will just only show here, it's, all these mathematical studies which are behind. Like, I'll just give some titles like elliptic problems and unbounded domains, solvability, and all that, existence stability. But what we are mostly interested now is the speed of propagation of this traveling waves. And I will explain a little bit later why we are interested in that, why it is important. But using all this mathematical development, in fact, and we can find the exact analytical expression for the speed of propagation. It's not so often that in complex nonlinear problems we can have an analytical answer. Here it is possible. We can find here this formula shows us the exact analytical value of the speed of propagation and how it depends on parameters. Why it is important? So I return back to this picture showing the experiments for two virus variants of SARS-CoV-2 infection for Delta and Omicron variant. Again, what is called plaque growth assess, plaque assess. So if we consider this white areas filled by dead infected cells, how fast it grows in time, right? So it is known in the biological literature that the size of these plaques correlates with virus virulence. So this is what we should understand here. We take these experiments, we look at these plaques, we measure their size, and the larger the plaque is, so the more virulent is the virus. This is very important. For example, of course, it depends on virus type and also on cell types. For these particular cells considered here, in fact, it's human lung cells. We see, for example, here that these plaques for Delta are much larger for Omicron. And this corresponds to the virulence of this variant and to. So again, this plaque size, in fact, how fast this infection wave propagates here in cell culture or in other cases in cell tissue. So how fast this plaque, this white zone, how fast it grows. But this is exactly the wave speed. So we conclude the wave speed, the speed of infection wave it correlates with virus virulence. So this is important. And this shows how this mathematical modeling can really evaluate some properties of viral infection. For example, this is a photograph of infected lung, and these yellow zones here show the parts of the lung which are like damaged by this COVID-19 disease. So in fact, the size of these damaged areas are determined by the speed of this infection wave propagation. So the next question is about viral load. What is viral load? If we consider this, for example, cell culture for some fixed moment of time, and we have we find the total concentration of virus in this culture, and mathematically speaking, it is the integral of our solution with respect to the space variable x. So this integral with respect to x is a function of time. So then we can determine how this viral load depends on time. And and here in this right figure, you see this blue curve. It's direct numerical simulations of this model, and green curve, it's an analytical approximation, and red curve is another analytical approximation. And in fact, this red curve is viral plaque during the wave propagation. So what is also important here to observe? We look at this blue curve, and clearly it has 3 different stages. So this is a function of time, how viral load depends on time. So clearly there are 3 different stages. In the first one, it decreases linearly, but in the logarithmic scale. So in fact, it's an exponential decay. So this first exponential decay is related to time delay in virus replication in the infected cells. So it takes usually several hours before infected cells begin to produce new viral particles. And during this time, virus concentration decreases exponentially. It's shown here. Then at the moment of time when infected cells begin to reproduce new viruses, many of them do it at the same time. This is why we see here very fast growth, kind of explosive growth of this virus concentration. It's the beginning of the process when this virus begins to replicate. And then it's the second stage. And then the third stage here, it converges to some, well, there are some details, but making it simple, to some constant value. This corresponds to the wave propagation. When the wave propagates, you remember this spike of virus concentration, it moves in space, but the integral of this virus concentration does not change in time. This is why this is constant. So we have the three stages of infection progression, and we can characterize all of them with the numerical and analytical methods, and even sometimes explicit formulas. In particular, well, of course, I will not stop on that. It's a quite simple analytical development. I will not stop on that, but it gives us at the end the exact analytical value of this viral load during this last stage of the wave propagation. So why viral load is also so important? Simply because it determines the rate of infection transmission. And if we discuss respiratory viral infection, then viral load in the upper respiratory tract determines the rate of infection transmission from infected individuals to uninfected individuals. This is well documented in the existing literature, the correlation between viral load in the upper respiratory tract and disease transmission, and we can determine all these characteristics in mathematical models. And then when we have developed all these models and these approaches, it is of course interesting to compare them with the experimental results, and we did it for different virus types. And here I will show only one example for this SARS-CoV-2 virus, and for two different variants, Delta and Omicron. And we, at this left figure, these are experimental results for the culture of epithelial cells. And this red curve, in fact, not the curve, but the dots, these are experimental results. The curve, it's modeling, we feed the data. What is interesting here is that the model is quite simple. There are only, in this model, only three equations, few parameters. Some of these parameters can be evaluated independently. Remaining parameters, 2 or 3, we can determine from this fitting of experimental data. So it, well, I wouldn't say that it is like the unique set of parameters, or it is very precise, but I think it's quite precise, this parameter evaluation from the experimental data. And we see here how it is different for this red curve Omicron and for this blue curve for Delta. In particular, we can see here that Omicron starts earlier in the epithelial cells, so its viral load is larger in the epithelial cells. This is why Omicron is faster transmitted between in the population from infected to uninfected individuals. Delta has less transmission rate. This is in epithelial cells. If you then look at the lung cells, the culture of lung cells, this is a little bit different. The curves are more close. But then we are interested not only in viral load, which can be found from the experiments, but also in the speed of propagation. So we have this experimental data on viral load. We feed the data, we determine the parameters of the model, and when we have the parameters of the model, we can determine the speed of propagation. Why it is important? Because, as I mentioned before, it is related to virus virulence and disease severity. So if we take these epithelial cells, we determine the parameters, we determine the speed of propagation for Delta and for Omicron. In this case, the speed of propagation of Omicron is faster, is larger. So in epithelial cells, in particular in the upper respiratory tract, so the speed of propagation of Omicron is faster, and this is why, in particular, not only viral load is larger, but also because of the speed of propagation, the incubation period for Omicron is less than for Delta. So it is more infectious and less incubation period. But if we take the culture of lung cells, these viral loads are quite close, so difficult to say. But then we identify parameters and we find the speed of propagation for both of them now in the culture of lung cells. And what we obtain? We obtain that Delta propagates in the lung cells faster than Omicron. So the virulence of Delta and disease severity of Delta in the lung cells is larger than for Omicron, and this is exactly what is observed in the clinical data. So the next question is about competition of virus variants. This is a very interesting, intriguing question. It's in the beginning of this year, January, February, there were some first experiments published according to the competition of these two variants, Delta and Omicron, and then we were inspired by these experiments to study this question mathematically with mathematical modeling. And again, the model is quite similar to what we considered before, but okay, we can look at the left or the right, not important. So we have, as before, we have uninfected cells, but then we have two types of infected cells. First type infected by first virus, second type by second virus, and then we have these equations for the concentrations of these two viruses. So the same, basically the same ideas, but now we have two viruses. We can do this, all this modeling, and we can compare these two viruses. So let us consider put the question like that. We have cell culture, and we introduce in this cell culture two virus variants at the same time. What will happen? And the answer is very precise. I formulated this almost as a mathematical theorem, but in fact it is not theorem because we cannot prove that. But we verified it by numerical simulations for a very wide range of parameters. So from this point of view, we can give a very precise formulation. So if there are two viruses in the same cell culture, we take their individual spreading speed. What means individual spreading speed? We take only one virus, we put it in the culture, and we measure its speed of propagation, as we discussed before. Then we take the second virus, we do the same. We have two individual speeds for these viruses, and we compare them. And the answer is that the virus for which the individual spreading speed is larger will dominate and will eliminate the other one. Well, this is quite simple statement. So the virus with larger individual speed of propagation wins the competition. I emphasize that it's not viral load, it's the speed of propagation, because in the biological literature, well, there's kind of confusion. Of course, in biological literature, the speed of propagation is not discussed at all. It just does not exist there. Everything is reduced to the viral load. So what I'm trying to explain today is not that there are two different characteristics, viral load and spreading speed, and they are responsible for different infection characterization. In spreading speed, it's virulence, or in the other words, severity of symptoms, and viral load, it's infectivity. So here it's speed, the spreading speed, which is important. So virus with larger spreading speed wins the competition. So this is our modeling result, and this is and then how to check that? We have determined this individual speed of propagation. So we know the answer from the modeling, but the answer, of course, depends on cell types. As I said before, in epithelial cells, Omicron spreads faster. We expect that in epithelial cells, Omicron will dominate and eliminate Delta, but it is opposite in lung cells where Delta spreads faster and Delta will dominate and eliminate Omicron. And then it's exactly what we have in the experiments. Not we have, of course, but from the literature. Well, I will not stop on the explanation of these diagrams, but it's exactly what I say. At the left, it's human nasal cell epithelial cells, and here it's Omicron, which wins, eliminates. Its Omicron is this violet bars, green Delta, and in the lung cells, this is opposite. So to conclude this, first big part of my today's presentation, so what we should learn from that is that infection spreads in both in cell culture, tissue, even in vivo. It propagates as a reaction diffusion wave. This infection wave is characterized by two main parameters. It's the speed of propagation, which correlates with virulence and symptoms, and viral load, which correlates with transmission rates. And that there are three stages of this infection progression, as we discussed before. And in the second part of this presentation, I will discuss the next step of all this modeling. So now we really consider how it happens in the human body and in the human airways, and the relation between viral infection and mucous motion and lung obstruction, which was, of course, a very serious issue for this COVID-19 disease. So a very short introduction again. Well, here at the left, you have the schematic representation of the lungs. There are, in fact, many generations. In fact, usually they say 22 generations of this bronchial chi. And of course, these airways differ very strongly in different generations, from very large ones, as you see here, 2.5 centimeters in diameter, 18 millimeters. No, it's not 18 millimeters long. I don't know what is 18 millimeters anyway, because it is probably longer than that. Anyway, so many generations. And then the last generations become very small. What is important for us now is that in the first 16 generations up to here, there is this fluid called airway surface fluid, which is produced. Shown here at the right, this airway surface fluid, it contains two fluid layers: periciliary ciliary fluid, which is low viscous, it's like water, and then on the top of it, I will show it later, this is mucus, very viscous fluid. So why it is so important? This fluid, airway surface fluid, it plays a very important physiological role. So in fact, there's a flow of this fluid from the bottom up, and this fluid protects our lungs from infections, from contamination, from different things. But if something goes wrong, this fluid begins to accumulate in the lungs, and this causes very serious problems, because the patient has difficulty to respirate, and at some point, if there is really too much of this fluid produced, then there is a complete lung obstruction. This is, of course, very dangerous. And this is what is observed in different diseases, and in particular for this COVID-19. Okay, so, well, I have already not much time, so I will accelerate a little bit. So this epithelial cell layer shown at the left with goblet cells, which produce mucus, and with this cilia cells, you see covered with the cilia, larger here at the right. So what is very interesting, it's really amazing how it works. The cilia have kind of coordinated like sinusoidal motion, and it pushes, this motion pushes the fluid up from the lungs towards trachea. Then more precisely how it works, you see at this right figure, there is this, in fact, 3 layers, periciliary liquid, then mucus, and then in between traction layer and the cilia, they come to this traction layer, and the motion pushes all this fluid, and it is important that exact coordination of all that, of the cilia and of these 2 layers, because if cilia goes too much in this mucus layer, since mucus is very viscous, then cilia just cannot push it. So all here is very, very well coordinated. So at the left figure, we see here this, of course, schematically, these different lung generations, but in modeling, we put them together. So we bring all airways from each generation together, and we obtain this kind of computational domain, which is like that. And then we do next simplification. We consider 1D approximation just in this, here it's this vertical direction, where it is possible, because though the width changes, the width enters the model, but the motion basically occurs in this direction. In fact, we started to develop such kind of models many years ago for another disease, in fact for a disease called mucoviscidosis, but now we bring it together with infection. Why infection is so important? Because viral infection and also inflammation related to viral infection, they increase mucus viscosity. This is shown schematically here. These viral particles, they initiate mast cells. These mast cells produce different inflammatory agent, TNF-alpha, interleukin-1 beta. It's very strong inflammatory cytokines. And both this inflammation and viral infection itself, they change the composition of mucus produced by goblet cells. And in this mucus, there are this, it's called this mucin molecules. There are many of them, many different types of these mucin molecules, and due to inflammation and infection, the composition change. In particular, there is increased concentration of this 5AC and 5B, which correlate with more viscous mucus. This is very important. And another point, but I will not discuss it really today, is that not only mucus is more viscous, but there is also hypersecretion. There are more mucus produced because of the co-infection. And then very shortly about the models. So there are 2 submodels. One submodel for infection that is very close to what I discussed before, but now we have to consider virus concentration in the cell layer and in the fluid layer. So there are in fact 2 different virus concentrations. And then second submodel is for mucus motion, also very shortly. So basically it contains 3 equations. The equation for the thickness of the mucus layer, and it's kind of transport equation related to, well, this advective term and mucus production here. And also the second equation for mucus viscosity, because of course we need to take into account, because if you look at the right, mucus production, it is different. The viscosity is different for uninfected cells and infected cells. So we have also here this convective term and diffusion term. And finally, how flow velocity is related to mucus viscosity. And if viscosity becomes very high, you see here, if mu, there's some maximal viscosity, and if just viscosity of the flow approaches this maximal viscosity, then the fluid, the flow velocity goes to 0. This is very important in this model, because it's exactly what happens. So then if we consider constant viscosity, then we have this kind of distributions of layer thickness depending on the space variable. Space variable here, it's lung generation. So from 0 to 25 centimeters is all these 16 generations. 0 it's largest, 25 it's smallest, and mucus thickness, you see here it's large, then it drops here. Why it drops each time? Because when we pass from one generation to another generation, the total width of this generation, in fact, changes. It is larger here than here. So the largest width, total width. So the last generations, they are very small, but there are many of them. In fact, 30,000 of the smallest generations. If we take the total surface of these generations, so the largest is here for very small airways, and then it decreases this way. And since it decreases, the thickness of mucus layer increases. So, of course, very schematically, very shortly, what happens here. Hopefully, it's clear because I already need to conclude soon. So, what happens? Then we take this model with this infection part, fluid part, all that, and we do simulation. So, what we observe? As we discussed in the first part, there is this infection wave which propagates through all the generations. And we consider from the first generation to generation, like about 12, it's not very precise, but about 12. It's shown here, this red curve, it's distribution of infected cells. So the last point at 24.5 centimeters is the total length. So you see, we are very close here. It's about 12 generations here. It's about 90% of the length. And infection, so infection is almost already everywhere if you consider the length of this total length. But nothing happens in fact, from the point of view of mucus motion, because, well, mucus changes like about twice, but the viscosity changes about twice, but it's not important because flow velocity is almost the same. Well, the width of the mucus layer increases a little bit, but it remains much less, orders of magnitude less than the diameters of the corresponding airways. So we see here there are 16 generations of these airways with their lengths, with their diameters, and with their numbers. But whatever, we took any generation, we compare at this first stage, we compare the thickness of the mucus layer with the diameter, and the thickness is much less, so there is no problem. So we can see, and this is like 90% almost everywhere, but this almost is very important. Why it is important? The explanation is very clear and very simple, because the most part of mucus is produced in the last generations. Why in the last generations? Because the total surface of the last generations is much larger, and mucus production rate is less in the small generations than in the large generation. But the total surface is so large that the most part of mucus is produced here in the large generations. But infection is not yet arrived to the large generations. So the most part of mucus has still normal viscosity. This is why at this first stage of propagation, though it is longest in time and it it covers almost the whole length, but it doesn't change essentially mucus viscosity and mucus velocity and thickness layer, exactly because the most part of the mucus is produced here and it still has normal viscosity. The second stage, now we have this last generations, and it quite fast, since the length of the generations is small, it takes only several hours more. Infection passes through these last generations, and now all mucus become viscous. So infection is everywhere, all mucus become viscous, and right away during several hours, the viscosity increases everywhere, flow velocity drops down very dramatically. So in fact, during the several hours, mucus plaque is formed. So mucus well, I just simplify a little bit, but to make it like clear and simple, after that, mucus does not move anymore. So the plaque is formed. But the thickness of mucus layer is still small. It's still much less than the diameters because it's too small time after the formation of this plaque. And finally, the last stage of this process. So mucus doesn't move anymore, but it is still produced everywhere here. So, and in fact, the model, so if we put in the model zero flow velocity, the model greatly simplifies. We have an analytical solution, and we see that mucus thickness here is a linear function of time. And after some, so this bold line, it's mucus, the thickness of the layer. It's a linear function of time, and several days, I mean of physical times, several days after that, the thickness of this mucus layer becomes comparable with the diameters of the corresponding airways. We do this estimate, and we see that exactly here in this last generations, like 14, 15, in these generations, after some time, the thickness of the mucus layer becomes comparable and then equal to the diameter or to the radius of these bronchioles, and it gives. And what this means? This means that we have a complete lung obstruction, which occurs in these last generations of airways, and it is exactly what is observed in COVID-19 patients. This plaque formation, viscous mucus, and lung obstruction in small airways. Well, to conclude my today's presentation, I think this is time already. So what we need to keep in mind, that infection spreads in cell culture, tissue, ex vivo or in vivo as a wave, and there are two important characterizations of this infection wave. It's speed of propagation and viral load. The mucus viscosity increases in the infected tissue. When this viscosity is high enough, then mucus flow stops and mucus plaque is formed. So then layer thickness grows more or less linearly in time because mucus is produced but not removed by like mucus transport, and after some time we have this airway obstruction. So these are several references. In fact, what I presented here, it's our recent works mainly published during this year. Some of them are only submitted. So thank you very much for your attention.
Thank you very much. Thank you very much for this talk. Well, just a comment before I take the questions from the audience. Just to be clear on that, so the mathematical model at the beginning is suggesting to run the experiments and study the speed of the front in which the virus is propagating on cultures, or is it that the mathematical model is trying to reproduce that phenomenon?
Well, unfortunately, we don't have a possibility to do experiments ourselves, so we use experiments published in the literature, and we use these experiments to validate our models and then, well, to determine parameters and to make some predictions. Well, when we do these predictions, they remain quite theoretical predictions. We don't have a possibility to verify them experimentally.
Okay, thank you. Any questions from the audience, whether online or in the room?
Well, can I just ask a question myself? So while people thinking, in fact, listening to Nader's talk, and I have questions to both of us. In fact, I was thinking about that before, but it's a good occasion to ask this question because Nader talked about atherosclerosis, I talked about infections, and in particular this COVID-19. What is known now from the recent literature is that COVID-19 reinforces atherosclerosis. So this is also very important because this infection it concerns also this endothelial cell layer, as we now very well know, through this ACE2 receptors, and they increase inflammation of this endothelial tissue, endothelial cells. And now from Nader's talk, we know that this inflammation, it's directly related to atherosclerosis. So this is why it is also observed that in COVID-19 patients, atherosclerosis can develop faster. So it's not really a question, but it's a suggestion to think about, to
couple the two
to both of us and also to other people interested, that to bring together these two questions. I think this is interesting study. Thanks. This was my question to my own talk.
Well, Ghada, please go ahead.
Hello, Professor.
Yes, hello, Ghada.
Hello. I have a small question.
Yeah.
Talking about involving two viruses in cells, the result was that one of the viruses wins. So what, from the mathematical point of view, inhibits the other virus from evolving? Or
Yeah.
is it a term coupling the evolution between both viruses in the system?
Well, in fact, viruses compete for uninfected cells. They compete because they reproduce in the same cell. They cannot reproduce at the same time in the same cells, so they compete for cells. So virus which infects most cells, it is reproduced more, and finally in this competition it eliminates another virus because another one does not have enough uninfected cells to replicate there.
Okay. Okay, thank you.
Thank you. Well, Youssef.
Okay, thank you for the talk. So it's Youssef Marie.
Yeah. Hello.
Okay, so yeah, as you say, so yeah, you consider only competition for the uninfected cell. So for this strain of COVID, there is no competition between the virus themselves, and also no cooperation to invade faster.
Well, in fact, you know, when well, there is a big domain in this field called co-infections, and in fact, there are many different co-infections when there are two viruses in the at the same time, for example, in the human body or in the culture, and there are many different ways how these two different viruses can interact with each other. They can compete, they can cooperate, and this is extremely complex, really very, very complex, because it also depends on what time, on timing, which one appeared first, then the second appears at the same time or a little bit later or much later, and the result of this competition strongly depends on that, because behind also all this biochemical machinery, all these cytokines, molecules involved. So this is really very complex. So, of course, our model from this point of view is very simplified because we don't consider here all this like biochemistry behind. So we like take only the first level of this virus interaction through uninfected cells. If you look at the first equation here, uninfected cells, you see now here there are two terms how uninfected cells can become infected through the first virus or through the second virus. So I agree that this model, of course, is simplified, but we need to start somewhere. But the second part of your question, we don't know, well, I don't know exactly from the biological literature if we take two different variants of the same SARS-CoV-2 virus, like, for example, Delta and Omicron, is there only competition for cells, or whether there's also some other interactions between them, I just don't know. I cannot say.
Okay. Yeah. Thank you.
What we can conclude that even for this model, the results we obtain, they correlate with the experimental results. But I agree that there are many questions behind.
Well, thank you very much. Let's thank the speaker again. Thank you very much, Professor Volpert, for being with us this morning, and we look forward to you being with us also in the afternoon session during the roundtable. Thank you very much. So we have almost 13 minutes break, and then we come back.
Okay, thanks. Bye.
Thank you very much. Thank you.
Who is a senior researcher at the INRIA at Lyon in France. So Mostafa will talk about modeling the relationship between antibody-dependent enhancement and disease severity in dengue infection. The floor is yours.
Okay, thank you very much. First of all, I would like to thank the organizers for the invitation, and sorry for the delay for this problem. I will talk about modeling the relationship between antibody-dependent enhancement and disease severity in secondary dengue infection. I am talking about dengue, but not from epidemiological point of view. It's at cellular and immunological level. I will explain during my presentation what antibody-dependent enhancement is. Yes, second page. As you probably know, the dengue virus is transmitted by mosquitoes. Some patients may develop dengue fever, or more severe, what we call dengue hemorrhagic fever, that can cause bleeding and drop of blood pressure. Then what we call dengue shock syndrome, which is more severe, and it is estimated that about 500,000 of dengue hemorrhagic fever occur each year, with 25,000 deaths, mainly children. And there is no yet effective vaccine for this disease. The virus has 4 serotypes due to mutations, sharing 80% of genetic homology, and this increases the risk of dengue hemorrhagic fever. The main hypothesis to explain dengue hemorrhagic fever is what we call antibody-dependent enhancement, which I will explain later. Dengue hemorrhagic fever can also occur during the first dengue infection in babies under 1 year due to antibodies received from their mother. Antibody-dependent enhancement is a phenomenon in which the binding of antibody, rather than blocking it, facilitates the entry of the virus into the cell and promotes the infections. Okay, here you can see in this graph some data about the incidence of dengue fever and dengue hemorrhagic fever in Brazil between 1986 and 2011. And we can see the year of the appearance of each mutation of dengue, each serotypes, the 4 serotypes, and this is increase the number of dengue fever and also dengue hemorrhagic fever. The dengue fever, it's in blue, and dengue hemorrhagic fever in red. And now all 4 dengue serotypes are now endemic in Brazil, which increases the risk of dengue fever and dengue hemorrhagic fever. For example, in 2019 in Brazil, we have more than 2,100,000 cases of dengue fever. Okay, second page, please. And it is interesting to see the history of dengue epidemics in French Polynesia, because this island is isolated with homogeneous spread of the disease. And this offers a good model to study the impact of the 4 serotypes. The story of this disease started in 1944 with dengue number 1, which reappeared years later and again years later, and also in 2001. And we can see also that dengue number 3 appeared 3 times, and finally dengue number 2 appeared twice. What is interesting here is that almost the whole population of this island has been in contact with the 4 serotypes. Unlike, for example, in Brazil, where epidemics reappear, but not especially in the same region. Okay, next slides. Here we have data on dengue number 1 in French Polynesia in 2001. And we have the ages in years of patients with dengue fever, dengue hemorrhagic fever, and also dengue shock syndromes. And we can see by model distribution of ages with 2 peaks. The first peak is at 1 year, and the second peak is at between 4 and 11 years. The second figure is a zoom of the first peak, and it is in months. The first figure is in years, and the second is in months. And we can see in the second figure, there is a peak of dengue hemorrhagic fever and dengue fever and shock syndrome and dengue shock syndrome between 6 and 10 years. I will explain, I will make a difference between the first and second phenomena because it's not completely the same. That means there is a difference for babies under 1 year and children for more than 1 year, and also adults. Okay, next slide. We take the first graph and we compare it with the dates of the 4 dengue serotypes in French Polynesia. And we can see that the risk of developing dengue fever is high in children with age between 4 and 11 years. This corresponds to the children born between 1990 and 1996. This is due to the fact that they were exposed to dengue number 2 or dengue number 3, which is different from dengue number 1. This is why we have this high risk. On the other hand, the risk is very low for people over 15 years old. Why? Because they were born before 1988, and they have already been exposed to dengue number 1, which was between 1988 and 1989. That means they are protected against dengue number 1 because they were already exposed to this serotype. And we can see also children with age between 1 and 3 years, they born between 97 and 2000. They are at low risk because they have never been exposed to any dengue. For babies less than 1 year old, it's their mothers that have been exposed to different serotypes because we suppose that they have more than 18, almost all of them have more than 18. And that means they were exposed to dengue number 2 and dengue number 3. The peak is between, for these babies, between 6 and 10 months. I will explain this and make a difference between babies and adults. Okay, to understand how antibody interacts, to explain this phenomena and how antibodies interact with the virus, I made here a representation in this figure. In fact, the antibodies can bind to the virus, and we have 3 situations. High affinity on the left, that means the antigen of the virus, high affinity to antigen of the virus, and you have also in the in the center, a low affinity, and in the right, no affinity. The high affinity means that the antibody recognizes completely the virus. That means it has already met and it binds to it strongly. No affinity means that the antibody has never met the virus and it ignores it completely. And on the other hand, the low affinity means that it recognizes it partially and binds weakly to it. That means it's not the same, it's the same virus, but not the same serotype. They have, as they share 80% of genetic homology, it can bind, but not completely. And with low affinity, the antibody do not neutralize the virus, and they don't let place to the antibody that can neutralize. And this is, in the same time, this antibodies allow the virus to easily enter the host cell and increase the infection. This is the explanation of why for dengue virus, if we are exposed to two different serotypes, this increase the occurrence of dengue fever and also dengue hemorrhagic fever. Okay, next. Here it's only to explain how it works. For the high affinity to have neutralization, antibody can neutralize the virus by binding completely to its receptor and not allowing it to interfere or to communicate with the cell receptor. Then the antibodies block the entry of the virus into the cell. Next, please. In this this figure, this is a representation of a virus. Each virus has a number of spikes. This is this, for example, for this one, which is HIV virus, they have 11, 10, 12 spikes on the surface. And each, for example, for dengue, there is 60 spikes, and each spikes has a number of what we call epitopes. In general, it's 2, 3, or 4 epitopes. Here we have for HIV 3 epitopes. And what we call paratope is the part of antibody that bind to an epitope. They don't have exactly the same epitopes as the virus, but there is like a receptor from epitope to paratope. In this example, we have antibodies that bind to epitopes and others that are free. But in my presentation, I will consider that the bind is uniform, not to have this kind of, to make a difference between 2 or 3 bind and 1. Okay, here we use a basic concept of chemical reactions to model how antibodies interact with the virus. We consider the chemical reaction in which you have N paratopes of antibody that we call P that bind to 3 spikes that we call S of the virus. Of course, what I put before, it's only a representation because epitopes and paratopes are in fact proteins. This is the chemical reaction, and you have a free and occupied spikes. At the end, at the equilibrium of this chemical reaction, the concentrations of free and occupied spikes are given by the second expression that use concentrations, where K is the equilibrium constant. We suppose that the total number of spikes is constant for each virus. That means, for example, the example here we have for HIV we have 12 spikes that we suppose that it's constant for each virus, the same virus, of course. Then we have the sum of concentration of occupied and free spikes constant. The concentration of S and free are equals to constant. Next, please. That means the fraction of occupied spikes is given as a function of the concentration of paratops P. We assume that the antibodies has the same number K of paratops. For example, in the example that I give, each antibodies has 3 paratops. The antibody concentration is then directly proportional to paratop concentration. Each antibody has, for example, 3. We obtain the fraction of, we divide by the same expression, and then we have the fraction of occupied spike as a function of antibody concentration as a Hill function. And we have the fraction of free spikes with it's the end F of A is 1 minus occupied spike. Here it's important because, as I told you, how the antibody neutralize the virus, it's because of the antibodies occupied the spike. And we need this, chemical reaction to understand how the antibodies occupied the spikes of the virus. Next, please. Knowing, now we know that how the antibodies, we know the fraction of occupied spikes by antibodies, then we have to define how this antibody neutralize the virus. I consider here a simple case. We multiply this fraction of by a constant beta. I consider here only easy case where beta is between 0 and 1. This is the simplest case. We can, of course, consider more complicated case. This is what we call fractional inactivity or neutralization of the virus. And you can see that if you put A go to plus infinity, you will have beta. That means beta is the maximum of neutralization of the virus. If beta equals to 0, there is no neutralization. And also if A is equal to, if there is no antibody, there is no neutralization. And we can see that this function is an increasing function in terms of A. And we can define also the opposite, what we call activity of the virus by 1 minus n beta of A, and it's given by this expression. And you can see that if beta equals to 0, which is the limit case, you have no neutralization, but you have complete what we call activity equals to 1, what we can call enhancement. Yes, thank you. Now I will talk about when we have this low affinity, what happens. That means the chemical reaction is not complete. The antibody do not interact completely with the virus. And they interact only with the P epitopes instead of all of them, instead of N. And we have what we call relative fraction of occupied spikes at the end of the reaction. And this is given by the fraction here that we call E. And we can see that if P equals to N, that means we have completely occupied. In that case, we will have the same function that is neutralization. That is, the opposite of neutralization, activity of, full activity of the virus. This is, and we can see that this function is different from the other one when the antibody occupied only a part of epitopes because we have an increasing function that go to maximum and decrease to 0. If there is like a window when the antibody that has a low affinity promote the infection and promote the virus to enter inside of cells. Next, please. Now I will use this chemical reaction and the data from Vietnam that I show in for babies to understand the relationship between this antibody that cannot neutralize the virus and the occurrence of dengue hemorrhagic fever. We consider here a model for babies under 1 year of age who have not yet developed their own immune system. We have data for this baby. You have the first column, the maternal antibodies that comes from different serotypes, and they cannot neutralize the virus. The second column is the age, the real age of dengue hemorrhagic fever. This comes from data. The third column is the predicted age of dengue hemorrhagic fever that I will explain after. And the last is there is a difference between these two ages. It's we can see that it's around 2 months. First of all, we predict the age of dengue hemorrhagic fever because we know how much antibodies the baby has, and as he didn't produce any new antibodies, there is only a decrease of this antibody, and we know the half-life of these passive antibodies is about 35 days. Then we can, it's exponentially decreasing. You have the equation here with the rate alpha. Then we can estimate around 10 molecules. Why 10 molecules is the amount of antibodies that are biologically defined to be under which the antibodies didn't interact with the virus and didn't protect the babies. And we can see here there is like, our objective is to explain this difference between the real age of dengue hemorrhagic fever and the predictive age, which is around 2 months. How in reality the data show that the real age of dengue hemorrhagic fever, it's not the one that we predict, it's 2 months later. Next, please. And we proposed a mathematical model to analyze this data. This work was published in collaboration with colleagues from Sao Paulo. You have B is passive maternal antibodies, which there is no production, decreases from initial condition. X is susceptible target cells, mainly macrophages and monocytes. Y is the infected cells. V is the free virus. And you have this function E beta is the infection rate that depends, we propose it like using chemical reaction, depends on the maternal antibodies. It is defined, as I said, using chemical reaction, and you have alpha, the degradation rate of antibodies. Nu is the consumption of antibodies by the virus. A, the production of susceptible cells. Nu1, Nu2, the mortality rates. Delta, the degradation rate. K is the production of the virus by infected cells. And you have C, small c is the fraction of susceptible cells converted to infected cells. And E0 is the rate of invasion of the susceptible cell by the virus if there is no antibodies, because the infection can occur also if there is no antibody, but the antibody here instead of neutralize the virus, promote it or increase the infection. And gamma is the fraction of virus-bound antibodies. Next, please. All the parameters come from literature except 4 parameters that are linked to this new enhancement. And these missing parameters are highlighted on the table. And we use the last data for babies to estimate these 4 parameters. Next, please. And yes, this is like a very quick mathematical analysis of the model using the same idea as in epidemiology. That means we use the next generation matrix to compute the basic reproduction number and to define, we have two steady states, disease-free steady states which always exist. That means the antibody disappear, virus and infected cells, only healthy cells go to an equilibrium. And you have also an endemic steady state, but the antibodies in any case will disappear because there is no production. And this endemic steady state exists if and only if the fraction of susceptible cells converted to infected cells is bigger than the threshold C0. And you have, of course, the endemic steady state exists if and only if R0 is bigger than 1. And we can give also the biological interpretation of R0. Next. Here, I will not prove this result, but I will prove only the global stability for the next model, which is more general. Here you have, of course, classical result. If R0 is less than 1, the disease-free steady state is locally asymptotically stable. And if R0 is bigger than 1, it is unstable, and the endemic equilibrium is locally asymptotically stable. And we have more than that. If R0 is less than the minimum between 1 and mu2 over mu1, mu2 and mu1 are the mortality rate of healthy cells and infected cells. For example, if mu2 is bigger than mu1, we will have R0 less than 1, but here it's more general, and also if mu2 equals to mu1. Then in this under this condition, you have disease-free equilibrium is globally asymptotically stable. And this is, we use a comparison principle and Lyapunov function. Next. Yes, this is only some numerical simulation. And here we have to be careful because to define what is the age of dengue hemorrhagic fever and the age of baby, because it's not the same. At time t equals to 0, the baby was born with a quantity of his mother antibodies. The antibodies decay exponentially, and the other solutions are constant. And the baby has been infected a certain time, then the antibody accelerate their decay. This is why you see this very quick decrease, and because of the consumption of the antibody by the virus. And the arrows indicate the exact time when the antibodies file to control the virus, and dengue hemorrhagic fever may occur. It is when Y is high. As the data, the model gives that the difference between the age of dengue hemorrhagic fever and the time when the antibodies file to control the virus, it's around 2 months. Because you can see that enhancement E, there go to a peak and the neutralization N fall down, and also the enhancement go to 0. There is like a small window between 4 and 6 months when the dengue hemorrhagic fever occur, when the virus is very high, etc. This is our explanation, and this is the explanation with these 2 months is due to the introduction of this enhancement function. There is a window when the risk is very high. Next, please. Yes. Of course, you remember that I use experimental data to consider the predictive age of dengue hemorrhagic fever. And in this data, we didn't take into account the consumption of antibodies by the virus to estimate the time of dengue hemorrhagic fever. But in fact, we can see that here the consumption, which is new, has no impact for the difference between the time of dengue hemorrhagic fever and the predictive age. This is why it was there is no problem to use this experimental data, which is independent of the consumption of the antibodies by the virus. We didn't take into account, and this is can be explained by this. There is no impact. Next. Yes, this is for the second model. That means for adults and children with that develop their own immune system. This is this work was also published with the colleagues from Brazil in 2021. Here there is a production of both antibodies. The antibodies A is the one that comes from the first infection with low affinity with the virus, and A2 is the antibodies due to the second infection. There is a production of antibodies A1 because there is these B cells that we have in the body after the first infection that continue to produce the antibody A1. And in the same time, when the infections appear, it increases this production. This is why you have, and it's not directly related to infected cells, but we put it here proportional to infected cells with this parameter alpha 1. It's only to make it easier, and you have a degradation of antibody and the consumption. And we can see that the antibody A1, due to a second infection, it's produced directly by the infected cells. And you have these two functions, A1 and A2, that I defined before for enhancement, the first one, and the second one is no neutralization. It's not the same meaning, but they have the same impact. That means, for example, if you see E2, if the antibody A2 are very big, this will be 0, will be low. That means more you have A2, less infection, that means neutralization. But the opposite for A1, there is a window, because if you increase A1, the enhancement increase, go to a maximum and decrease. There is this window that we have a risk of dengue hemorrhagic fever due to A1. Next, please. Yes, some mathematical analysis. We have also two steady state, disease-free steady state, which always exist. We use a next generation matrix to calculate R0, and we can also give biological interpretation of this R0. Of course, you have the existence of endemic steady state under the condition that R0 is bigger than 1. We have a local asymptotic stability of endemic steady state under the condition of R0 bigger than 1, and we use a classical root-Horwich criterion. And the main part, mathematically point of view, is the global asymptotic stability of the disease-free steady state when R0 is less than 1. We are expecting to have also global stability of the endemic steady state, but we are not able to prove it. Okay, next. I will give an idea how we prove the global stability of disease-free steady state under the condition when R0 is less than 1. And here we suppose that the mortality rate of infected cells and healthy cells is the same. This is why you have the same gamma. And to prove this, first we construct subset that we prove that it's invariant and globally attractive. This is when the first antibody A1 is bigger than his equilibrium, bigger than gamma 1 over lambda A. This set is invariant by the system and globally attractive. And if a solution stays out of this set, then the first component, that means the antibody A1 is increasing function, and the solution tends to the disease-free steady state. That means now we can stay inside of this set. If we suppose that there is a solution that enters into the set D at a finite time, they will, as this set is invariant, it will not go out. Then we work inside of this set D and we make a change of variable. We put B1 is to have positivity, etc. And we put also, we consider two cases. The case when the total population of cells X plus Y bigger than this threshold or less than this threshold. Yes, next. Then we first consider the case when X plus Y is less than omega over gamma. Then on the set D, the solutions satisfy this inequalities. Then we use a comparison principle. In fact, it's the same. We can use also monotone dynamical system. We will have the same results. This is, but we can do it directly. And we compare, next, please. We compare in the set D, we are able to compare our system to a linear system given by this one. And if we analyze this linear system, we can see that the characteristic equation is given by this expression. We have a negative eigenvalue and also two roots of the polynomial of second degree, and which by using root and Horwich criterion, the two other eigenvalues are negative if and only if R0 is less than 1. Then we have the minimum to have the global stability of the disease-free steady state, and by comparison principle, we have global stability of all the system. Yes. Yeah, it's not finished yet, because for the other case, if we, yes, sorry, next, I want to say that the proof is not finished yet. If we consider the case when the total population is bigger than omega over gamma, from the equation of Z is X plus Y minus gamma omega over gamma, we have for all epsilon and all initial condition the existence of time for which, and we can compute this time such that the total population Z of t is between 0 and epsilon for all t bigger than t epsilon. Then we can compare again our model to this linear one for t bigger than t epsilon. And if this system, if we consider the characteristic equation of this new system, we don't have R0, but it's what we call R epsilon. And you can see it's only if for epsilon equals to 0, you have R0. But in any case, under the condition R0 less than 1, we can choose epsilon small enough such that this R epsilon is less than 1. So the trivial solution of this linear system is globally asymptotically stable. And we conclude that the disease-free steady state P0 is globally asymptotically stable on the set D, as D is, if we are outside of D, we go, the solutions will go also to P0. We have global asymptotic stability of disease-free steady state. Yes, next. Now some numerical simulations. The rows indicate the time. This is very interesting because it's not, we are not interested, in fact, for biological point of view, we are not interested on the asymptotic behavior, because the dengue hemorrhagic fever, it's a transition. It happens a few days after infection, and we are interested only on the peak of the virus that we can see here, and it's related to enhancement when E is a peak. And in any case, if R0 is less than 1 or R0 is bigger than 1, we will have the same behavior. The only difference is for R0 less than 1, the population, all will go to the steady state. For the other one, they will go to endemic steady state, but the endemic steady state is very low. We can see it, for example, in this figure. We are not interested, it's the mathematical point of view, of course, it's good to make mathematical analysis, but what is very interesting is this transition period for a few days after infection. And we can have it here for the virus and the antibodies, and also for cell infected cells and healthy cells for these populations. I don't know how many times I have. It's almost, yes. Next, please. I almost finish. Yes, we make also, yes, I did talk about how to define the hemorrhagic fever. Is we calculate the maximum value of infected cells. And why this maximum is very high, we consider that it's dengue hemorrhagic fever. And also the time when this maximum is reached, at which it's not asymptotic. It's like some few days after when the virus appears. This figure is to analyze this maximum value of infected cells and the time in terms of alpha 1, alpha 2, which are the mortality rate of antibodies, degradation of antibodies A1 and A2. And you can see that we were surprised because we was thinking that we will have, especially when A1, we increase I1, we will have something monotone. It's not the case. That means if you increase the mortality of antibodies, the infected cells will increase, go to a maximum and decrease. And also the time when this maximum is reached. And this is very interesting. And you can see that there is a mortality rate of antibody that offer these windows when the maximum of infected cell is very high. And also the time can be very high or very short, it depends. And for the time, it's a maximum 2 days and a half. But for the second antibodies, we can see there is no surprise. It's the time is increasing and the infected cells is decreasing. That means the neutralizations works as we are expecting. Next, we have also this very interesting behavior of infected cells and the time when this occurs. If we consider the initial antibodies A1 that promote infection, you have like a kind of plateau between, we can see the blue and the red one. There is no change of, not too much change of maximum infected cells and the time. And there is a threshold when these infected cells decrease very quickly and the time increase very quickly. And this has no meaning biological point of view, because after 70 days of infections, in fact, the infection disappears a few days after. That means we have to see this first figure only for the antibody between 1 and 2.2. If we are out of this, that means there is no dengue hemorrhagic fever, because the maximum of infected cells drop to 0. And we can say also for R0, it's high when the antibodies, the equilibrium of antibodies that come from the first infection is not very big and not very small. There is a window. And this is very important. That means the time between the first infection And the second infection is very important because this time that make the decrease of antibodies that come from the first infection. Okay, next. Yes, there is some references. And thank you very much for your attention. Any questions, I am open to answer.
Thank you very much.
Thank you very much, Mostafa, for this talk. So floor is open for questions. Fatima, kindly help me with the audience
Yes.
in the room.
So any questions? Yes.
Okay, hello, I'm Mazen. I have a question about the linear stability. You study the linear stability, and what's about the nonlinear stability? I don't know if you are sure that the nonlinear system compares to the same point at the linear system.
Yes, this is using comparison principle, and yes, this is, in fact, it's kind of monotone dynamical system. And the comparison between nonlinear one, we compare the nonlinear system to another linear system. It's not linearization of our nonlinear system, but as we use this monotone dynamical system, we are able to compare our nonlinear system to a linear one. But it's not, I repeat, it's not the linearization of our system, because we take the maximum of the nonlinear part and not the derivative of this nonlinear part. It's okay?
I have another question, thank you.
Yes.
We see in your model the influence of mother antibody.
Yes.
And so it's possible to use immunotherapy by, I don't know, injecting some antibody from mother to to decrease the size.
Yes, this is I didn't talk about this, but Sanofi developed the vaccine, I think in 2000. I think 2015, and it was a disaster. Because they use this kind of, it's the same. And the problem with this dengue virus, you don't know which serotype will appear. And you have to develop kind of vaccine that block the 4 serotypes. It's different from influenza and from COVID, etc. And not to have the good antibody is very dangerous. This is why they use this vaccine in Vietnam, and after a certain time they were expecting to have the same serotype that come epidemic with the same serotype. It was not the case, and many kids has this hemorrhagic fever increased with the vaccine. And this is there is many people that are working using therapy with antibodies, but it's for dengue virus, it's very dangerous, and they do it carefully because you can promote the infection instead of blocking it.
Okay, thank you for this interesting talk.
Other questions from online audience, perhaps?
So probably we need to move to the second talk.
Yeah, sorry.
Sorry. There's one more question, I'm sorry.
Yeah, no, it's not a question. It's because maybe there is kind of understanding. The antibody that babies that comes from their mother don't help. It's the opposite, because they promote the infection. This is, I forgot to tell.
So please go ahead.
So it's you, Youssef. Thank you for your talk. I was just wondering, So in your model, you don't care which strain is the which strain is the first to infect the. So is there any kind of order if you are infected by strain number 4 first?
Yes,
and then
exactly. It's sure that it's different, but for data, they are not able to, how to say, all data that we have, they are not able to make a difference between, but it's sure that its serotype is different from the other. But all the data that we have, they don't make this difference between serotypes.
Okay, thank you.
Yes, you're welcome.
Okay.
Hello, Dr. Adimy. This is Ayman. Well, I have just a question related to the parameters that are specific to the virus, for instance, the number of spikes and other parameters. Can we see the role of such parameters in your results? And for instance, if we can try to apply the same strategy to other viruses, for instance, and to check the important role of the number of spikes and other parameters related to the virus itself.
You talk about chemical reaction, the parameters that comes from chemical reaction.
Yes, exactly. Yeah.
Yeah, this is the first time that we use this kind of model of chemical for this virus. I didn't find in the literature. Maybe it can be, but there is like a weak part of this. We didn't take into account the competition between antibody A1 and A2. You can see that I separate them because it's very hard. Maybe it can be good to make competition also between the two antibodies. And maybe, yes, it can be, we are working in this part and to see if we can use it in other disease that has the same.
Okay.
My answer is yes, maybe it can.
Yeah, this should be done. Yeah, that's interesting. Okay, thanks a lot.
You're welcome.
Okay. Perhaps we can move to the other speaker. Thank you, Mostafa, for this very interesting talk. And thank you for the questions, dear audience.
I stopped. Oh, no, it's okay.
So, Fatima, shall I introduce the speaker? Or you will do it?
Yes, please, we can start.
Okay. So let me welcome Mostafa Bendahmane. Is the starting time already started, or?
It is okay for me. Perfect.
Yeah, you can start, Nader. Yes, please.
Okay.
Oh.
Okay. So, it's my pleasure to introduce Mostafa Bendahmane for the next talk that is entitled Recent Progress on Homogenization of the Bidomain and Tridomain Models in Electrocardiology. Mostafa is a researcher at INRIA Carmen project, and the floor is yours.
Okay, thank you very much, Nader, for this presentation. Okay, first I would like to thank Fatima and Kams for this organization of this workshop. Okay, first I would like to talk about our adventure of homogenization in electrocardiology. Okay, it was started during the thesis of Fatima. We derived in this thesis, or Fatima derived in this her thesis, the Bidomain by using an elegant method on homogenization. This method named unfolding method. This method can be adapted to any domain. We can see that before in the literature or homogenization literature, the heart is presented as a cubic, and so it's not good. Our method is more strong because can be adapted for the geometry of the heart. After the thesis of Fatima, our work on homogenization was continued in the thesis of Fakhreddin Badr. And in his thesis, or thesis of Badr, was mainly devoted to modeling and also on multi-scale of Bidomain and Tridomain. His thesis is divided into two big parts. The first part is dedicated to macro, meso, micro Bidomain. Meso is an intermediate scale between macro and micro. When we add, for example, the mitochondria, and in the second part, we focus, or he focused in his thesis on the construction of Tridomain by using, of course, our unfolding homogenization method. Okay, our presentation, my presentation today will be will be focused on Tridomain model and also the construction of this model. Okay, my presentation will start with a basic anatomy and functionality of the heart and the cardiac cells. In second part, I will derive formally the Tridomain model, and the last part, I will construct rigorously our Tridomain by using a rigorous homogenization of unfolding method. Okay, this this talk or this work, this one with Badr, Mazen, Saad, and Rafat. Okay, I will start with this pictures. We know that cardiac contraction is triggered by electrical potential or electrical activation. The electrical signal starts in the sinus node, which is the natural pacemaker. And so we'll conduct a signal from cell to cell through the right of atria and spread to the left of atria until arrives to atrioventricular node here. And because of the presence in this region here, close to atrioventricular node, we have a fibrous atrioventricular. The impulse of the signal does not spread directly from atria to ventricle. So the only way to use is to travel from atrioventricular node to Purkinje fibers. And Purkinje fiber system is a network of schizoid conducting cells that carries the signal to the muscle of both ventricle here. I'm sorry, this is, we cannot see. I will just put, yeah, just here. Okay. And so the lesson here is that the signal or the electrical signal propagates across atria through atrioventricular node along Purkinje fiber system and through the ventriculars. 3D. The challenge here is to construct a complete model, cardiac model, that coupled all this model of 2D, 1D, 3D that can take into account of the particularity of muscles in atria, also fibers of Purkinje and muscle in ventricle. Here we have the profile of electrical potential or potential action potential, sorry. Here we have equilibrium, and after we have depolarization corresponding the flux of potassium, sorry, and we have also plateau. This is the fluxes of calcium, and also repolarization fluxes of sodium. Okay, after we have equilibrium of the cell, this means that the total current across the membrane is equal 0. Okay, I will continue with the next. Oops, this doesn't work. Yeah, okay. Here we can. This is. I have a problem here to see. Okay, we have here we have a zoom of at microscopic scale of the mass of the heart. We can see here that the end of cell join other cell and create a thickness or a membrane that allow ion to pass or to move through them. The second picture is this is a cardiac muscle of myocyte. We can see here that the myocytes are connected between connected end to end by here intercalated disc. Adjacent to this intercalated disc, we found gap junctions. Okay, and the gap junction allow potential to directly flow or spread from myocyte to another one. We need okay. Here we need to distinguish of two types of exchange or ion exchange in the media. The first one is intra-exchange between cell 1 and cell 2. The cell 1 and cell 2 are separated by the gap junction, the gap junction membrane. Okay, this is intra-ion exchange, and we have a second exchange between inside of cell, this means cell 1 and cell 2, and outside of cell. Okay, so cell 1 and cell 2 are electrically coupled through gap junction, and so we have action potential that propagate from cell 1 to cell 2. So now the exchange between intra and extra media. The membrane that separates here, the membrane that separates extra media and intramedia. Intramedia, recall that this is cell 1 and cell 2. The potential in extramedia will be denoted by UE, and the intramedia, the potential will be denoted by UE1 and for cell 1 and UE2 for cell 2. And their difference will give us a transmembrane potential that lives, of course, in this membrane that separates intra and extra media. Okay, this potential that lives, recall that the intra potential lives inside the cell, and UE extra potential lives inside of extra cell. And the difference between these two potential lives on the membrane. Okay, and so the transmembrane potential Vk is governed by this ODEs, where EM here is the total current through the membrane. The total is the sum of capacitive current and all electrochemical current. Electrochemical current are, for example, potassium current, sodium current, calcium current, and also I like current. All this electrochemical current depend on transmembrane potential Vk and also on next potential. And this the dynamic of transmembrane potential Vk is coupled by another variable, ODE, which modelize the opening and the closed of channel, also activation or inactivation of channel. CM here is the capacity, and IN is the current IN. And it depends if we work on atria, ventricular, or in Purkinje fibers. Now, regarding the dynamic between cell 1 and the cell 2, and then this will create a potential that will be denoted here by S, which is the difference between potential E1 and E2, the potential between cell 1 and cell 2. This, the gap section potential S, his dynamic is given by the following, or the E's, where EG is the sum, also the sum of total current, capacitive current, and E gap, or total unique gap current here, denoted by E gap. What is the lesson here is to follow my presentation, and also to understand what I will, when I will construct the Tridomain. We need to, Tridomain for me, it means that this means the first one is the first domain of cell 1, the second one is for cell 2, and the third is extra cell, or outside of the cell. This means Tridomain. So it's more important to understand what we mean by potentials extra, and also the potential in the gap ejection. Oh, okay, I will continue my presentation. Okay, next up. Okay, here in the literature we can find many unique functions. For physiological model, we can find the famous Hodgkin-Huxley model for neuron, novel for Purkinje fiber, LURD for atria and ventricular. IN is the sum of all electrochemical current. The phenomenological model is the Fitzhugh-Nagumo, Van Kappel, Mitchell Schaefer, where V here is for Fitzhugh-Nagumo, the ion function or ion current is a cubic on V, on transmembrane potential, and W. V here is normalized from the classical Hodgkin-Huxley model. In our study, we will, of course, in the literature, we will not find much more work on authors that work on also the coupling between transmembrane potential and also gap junction potential. So in our study, we will present our membrane of gap junction is like a passive membrane. So sorry for this E. So it has this form linear, where G here is the capacity or reverse of the resistance of the membrane. Okay, I will continue my next. Okay, here we have a collection of cells. Sorry, here we have a 2D section of some amplified periodic cell, network of cell. Section on the right is a section of the reference cell Y, that the sum of YA1 is the cell 1, YA2 cell 2, that are separated by the gap junction membrane, that this boundary is denoted by gamma 1, 2, and the boundary between cell 1 and the extra media is denoted by gamma 1, and between cell 2 and the extra media, the boundary will be denoted by gamma 2. Here we have a collection of cells connected end-to-end and side-to-side by junctions surrounded by extracellular media here. Okay, the cell 1 and cell 2 are separated by the gap junction, gamma 1, 2. to construct our tridomain, we idealize, of course, the microstructure of the cells. So cells have the same shape and are arranged in space in irregular fashion and have the same patterns. The epsilon here is the ratio between the micro and the microscopic scale. Okay, I will continue. Here we have the variable. Okay, the first one is cardiac tissue volume by volume. Here the omega is the union of medias, the first cell, the second cell, and extramedia denoted by omega E. Union all boundary. The first boundary here is the boundary of gap junction. Gamma 1, the boundary between first cell and extramedia. Gamma 2 is the boundary of cell 2 and extramedia. Okay, the intracellular media has some conductivity that is denoted by ME. MA. ME is the extracellular space with conductivity ME. Gamma K is the membrane of cellular membrane separated between cell K and extramedia with some capacity here, say MK. Sorry, it's missing here. K. Gamma 1, 2 is the gap junction membrane with some also capacity CG. UE and UA are the intra and extra electrical potential. Their difference is the transmembrane potential with some reference for K. W is the recovery or the recovery variable or gating variable. The difference between intra potential is the transmembrane gap junction potential, and IN is the membrane current. What the lesson here is VW, VKW, and IN are defined on the boundary that separate intracell and extramedia, and S here is defined on, of course, on the gap junction membrane. Now, after defining the variable, we will define our equations. Here we have in intramedia and extramedia, we have a quasi-static conduction or quasi-static equations. Laplacian is equal to 0. Then there's no much more variability in time of the potentials. Okay, in the boundary, here first, and the boundary that separate intra and extramedia, we have continuity of the fluxes. Similarly to the gap junction membrane, we have also a continuity of fluxes. Okay, and we complete the quasi-static equation and the continuity of the fluxes by a dynamical coupling or reaction surface condition on gamma 1 and gamma 2, and also in gamma 1, 2. The first one is for gamma K. We have here the total or the fluxes is equal to the total current. We complete this by the gating or recovery equation for W. On the gap junction membrane, we have this dynamical equations. Here we have the trace. The difference between intra and extramedia is the transmembrane potential defined in gamma 1 and gamma 2. And the difference between the traces of intramedia, of intra potential of this first cell and the second cell is the gap junction membrane potential. Okay. We complete, of course, these equations by no flux boundary condition, an appropriate initial condition for V and S, and the normalization condition of UE. Mean value in the domain of UE will be equal to 0. Okay, I will continue. Please, if you have a question, you can stop me, no problem. Okay, I will continue. Okay, here we will define the portion of intra-extracellular space of omega K intra and extra media by YA and YE. The solution UE and W have the following, sorry, I forget that to add also V and S, VK and S have the following asymptotic epsilon power expansion. So we can write these solutions as this form. Work C, the solution will be depend on microscopic scale and microscopic scale. And so here C is the microscopic variable, X is a microscopic variable, and we will use this or this full derivative operator. Our gradient here is with respect to two variables, X and C, and here we have Laplacian with respect to the micro and the micro scale. Okay, using this and put it in our equation, we will obtain the following microscopic system. So we collect the terms in power epsilon -2, -1, 0. We will obtain this three boundary value problem. The first one will give us a unique solution of UE0 that not depend on microscopic scale C. So UE0 will be depend only on microscopic scale. So it's not hard, and we will use this solution and we will put it in the second boundary value problem. This term will be equal to 0 since UE0 will be depend only on X. And so we will obtain UE1, a unique solution UE1 that depend on UE0 that we will put it in the last boundary value problem, and we will obtain finally our Tridomain model. Okay, the first regarding the first boundary problem. This problem has a unique periodic solution up to a constant, and so is not depend on C. And so we will be depend on only on X. So we will use this information in the second boundary value problem, and so we will obtain this elliptic equation. So this elliptic equation is not hard to see that admits well postulate the existence and uniqueness of a periodic solution UE1, and this solution can be represented by in this form. Our C here is satisfied the following epsilon cell problem, where UL here is or R the standard basis in R3. Now, using this information from the first boundary problem and the second and to the last boundary problem, and we will obtain this and using, of course, this we write it in the form of the fluxes here, and so we will integrate this equation with respect to cell portion YAK, and we will use the divergence theorem. We will get the following integration. See here that these two terms coming from the continuity of the fluxes from this two boundary condition. Okay, so since V0, W0 and the S0 doesn't depend on on microscopic scale, So we will obtain, we will arrive or obtain this equation for the first or for the intra electrical potential of media of cell 1 and cell 2, where the conductivity has the following form. Similarly, we can obtain also the motionless average for the solution of extra electrical potential that has this form. Similarly, we can obtain also for the gating variable W. Okay, now we have only the formal, we derived that this formal homogenization or derivation of Tridomain, that it is used frequently by the physician. So after I will prove it, I will prove this Tridomain model by using our strong method, unfolding convergence homogenization method. Okay, I will continue. Okay, here we have an history of, I don't know, I cannot put it, sorry, I cannot put this outside, this strange. Okay. Okay, here we have a short history on homogenization in electrocardiology. Okay, the first derivation of the rigorously of the Bidomain was used by Penacchio, Savary, and Franzoni by using the homogenization method the Georgi of gamma convergence after Kenneth Carlsen and his student Grandelius derived the Bidomain by using to scale for a unique function of physiognomo type and a cubic domain. After this work, Fatima, in the thesis of Fatima, we have proved or derived the Bidomain model by using unfolding convergence homogenization method. Use it for simplified ionic model or also physiological ionic model like RUDN or others but on any domain. Here we respect the domain, the hard domain. This we continue with this model and we applied in micro, meso, macro scale when we add mitochondria. And so the meso is mesoscopic. This means a scale intermediate between micro and micro scale. And we prove we derived a new Bidomain model when the conductivity is different to this obtained in the classical Bidomain model. And my talk was coming from the last work of our work on unfolding homogenization, of course, gap junction membrane. So I will give some an history that are not complete the origin of unfolding homogenization. Before to scale, we can find in the literature many homogenization method. For example, gamma convergence à la De Giorgi in 1970 by using operator theory to prove rigorously the convergence homogenization, the homogenization convergence. After Tartar and Murat developed a new concept of
Mostafa, we have to end soon, please.
I am sorry. I will. How much time I should have?
Well, and the program you have 40 minutes of talk. So now in 5 minutes it will be okay.
Okay. I'm sorry. I will jump this. Okay. The unfolding. Okay. The ingredient. The ingredient of homogenization method is the definition of the unfolding operator. This operator transforms a function of one variable into a function of two variables. So it is possible to reduce the concept of two scale conversions to a usual notion of weak and strong conversions in LP. Okay, we refer further to the work of Ionescu et al. I am sorry, but I have to take more time. Okay, this method is adapted to many problems. For example, can gives also a good corrector result under minimal assumption or regularity assumption. For example, of course, this method is well adapted for perforated domains. Okay, I will give just the definition of weak solution. And so the weak solution for microscopic is given if this has this form, UE and UE is in L2H1, V in L2H1 because V and S and W defined on the boundary, dt of this solution and also in L2 on the boundary, and satisfy the following weak formulation. Of course, from this equation, we can have only two weak formulation. And so, because we have continuity of fluxes, this can be added to the equations. Okay, I will. So for the difficulty degeneracies and also to prove the existence of solution, we need to work with non-degenerate problem. And so we will prove the existence locally of solution and after a global solution by using some a priori estimate, an appropriate compactness argument, and then we pass to the limit in n to 0. We have also a uniqueness in the case of microscopic scale. This means when epsilon just fixed. Now our goal is to pass to the limit when epsilon go to 0 and to obtain. So I will to obtain the Tridomain model. So we will define. I will just 2 minutes, please. Just okay. We define the unfolding operator like that. Here, the definition Z can be as the sum of its local position in the cell, and here Z here is gives us the location of Z in the cell where Z is. Okay, I will. And we have some properties of this operator, a linear, continuous. The unfolding of the product is the product of unfolding. And we have this equality of integral. So we can use the weak formulation for the microscopic and transform to unfolded weight formulation. And so we can pass the limit easily in this weak formulation. And this theta is a function that defined all integrals on the boundary, and theta go to 0 when epsilon to 0. Then we can pass, we can have some a priori estimates, and we can pass weakly, but we need to have strong conversions because of the nonlinearity, or because also in the case of Fitzhugh-Nagumo model, for physiological model we use Menti, and for Fitzhugh-Nagumo we use Kolmogorov compactness criterion. Okay, now we can pass to the limit in this unfolding formulation, and we have and we prove this theorem. And so we can see here that we have a new Tridomain model, and okay, we can talk probably in discussion because it is a time.
Yes. So
we can talk about this model with colleagues if they are interested on this. Okay, thank you very much for your attention.
Thank you. Thank you.
I'm sorry for the time.
Rich and detailed talk. So floor is open for questions.
Yeah. Thank you, Mostafa, and thank you, Nader. So any questions from the audience? Well, just a question regarding the cells, how they are constructed, the unit cell that you have constructed at the beginning. So we only see a gap junction between two adjacent cells, and then
here
earlier, yes, this one. So we only see a gap junction between two adjacent cells, and then from the other side, what happens? There's no gap junction, no?
It seems to me this is the gap junction follow the orientation of fibers. It seems to me that it is natural here. Okay, of course here we can. This should be also gap junction here, but the problem is we can not do homogenization in this case. We will break the periodicity. Okay, but we can. Okay, we can have, for example. The gap junction here, it is possible, but we need the cell Y will be, we need to add more intracells, and the variable will be explored. So we will have many variables to deal. And so this is why, for us, it's we simplify it in some sense. We simplify here the problem or the homogenization when we add the gap junction. Of course, this is not, we idealize in some sense here, we idealize our structure.
Yes,
I don't know if it is okay for you, Fatima.
Okay.
Please, Yusuf.
Okay, Yusuf now. So thank you, Mostafa, for the talk. So I have actually a general question for all the talk I have seen on cardiovascular model, but since you are the speaker, you will want to answer. So I was just wondering, so maybe the answer of my question is in the paper, but I didn't have time to see the details. So when you are looking at the cell, the microscopic scale, so you consider the transport, the ion transport, the transport only respect to the current potential. So I was wondering if also the active transport, the passive transport, the storage of ion inside the cell, and also the pump is taken into account in your model, or if not, if it's something important that should be taken into account. Thank you.
The transport inside is follows this quasi-stationary condition or equation. Okay, this is what we have. This is diffusion. If you want an intra-media and extra media. I don't know if this is your question, the answer to your question, or
it's about the flow of ions, right? Yeah. Well, the flow of ions. Let me answer this in place of Mostafa.
Please.
Ions is represented, yes, by the ionic function, and it depends whether you're taking a physiological model or a phenomenological model. So if you're taking a physiological model, every protein channel is taken into consideration in that.
Yes.
Any other questions?
Of course. Ion is just ion. Here, the function of ion is the sum of all electrochemical that I have seen before. Electrochemical current, sodium, potassium, calcium currents. Just this, or the movement of ion from inside, from one side to others. And that create, of course, it creates this potential on the membrane. Okay.
Okay. Questions
yes,
from the virtual audience?
Actually, I have a question, Mostafa. This is Ayman.
Hello, Ayman.
Yeah. You put some boundary conditions between the unit cell and the extracellular medium, right? So,
yes, the continuity fluxes. This is the boundary that you have.
Continuity fluxes, this is on gamma epsilon, which is between Y1 and Y2, right? Gamma epsilon. Yeah, this one. The
gamma epsilon, yes. This one, yes. This is between intra and extra cell. Yes.
And actually, the point is, what if we change the boundary condition? Not only we having this just continuous flux. So you have a kind of Neumann type, right?
Yes, here, this is here. We need, yeah, of course.
What if we change this boundary condition? What has as effect on your results?
We don't. Okay, in homogenization, okay, usually we use here Neumann boundary condition, of course, yes. But if there is no another condition of boundary, I don't see what is the meaning physiologically. What will be meaning if we change the fluxes here? You see my point? Here, of course, the continuity of the fluxes can be understood physiologically. This is the flux. Okay, the concentration we have. The fluxes in one side and also other side. This is the fluxes the entering. This can be.
Why not imposing that the potential is this? Let's say it's equal from both sides of the boundary.
Are equal. This means for you is to say that we have continuity of fluxes and also continuity of the potential. If you
exactly, not only fluxes. So this is a kind of mix between Neumann and directly boundary condition.
Yeah, but in this case, the potential will be equal to 0. The potential of transmembrane will be equal to 0. That is not good.
Okay.
Because if you assume that you have continuity, but the continuity of
because, sorry, for example, if we deal, for instance, with kind of fluid structure interaction problem, we don't only impose the continuity of forces, we impose continuity of velocities and forces both. So this was my question. Nader, you have got my idea, right?
I agree with you. And in this context of fluid, it's okay, but the context of the potential is not good because the potential will be equal to 0. This is not good if you add. But I will show you something. If we add, for example, here, okay, see here, from Tridomain, we can have the Bidomain, okay? Here, this is the case or an isolated cardiac model, okay? The heart is isolated. There is no connection between heart and thorax, or torso. We can have connection between heart and torso, and so we will have continuity of the fluxes and also the potential on myocard. This is in omega. You will have, for example, UE, the extra potential that will be equal to some UB, that is the potential outside of the heart. You see, this is it possible.
Okay, I see.
If you couple heart with the torso, yes,
with extra domain, yes, that's I see. Okay, thanks a lot.
No, welcome.
Do we have any questions from the virtual audience?
You can raise your hand.
No raised hands.
No questions.
Okay, so I think let's thank our speaker again. Thank you very much, Mostafa. Thank you very much also, Nader.
Thank you very much.
So we have a lunch break now, and then we will join later at 2:30 p.m. Beirut time. Thank you very much.
Thank you. Bye-bye.
Thank you.
Yeah. Okay. First, I would like to thank Dr. Fatima for this organization of this workshop, and thank you for this invitation. In this talk, I'm interested in the asymptotic behavior of solutions and the pattern formation of the nonlinear degenerate killer system signal modeling chemotaxis. This work is in collaboration with my colleagues, George Chamon, Mostafa Ibrahim, and Rafat Al-Houk. Our motivation here is to show the formation of patterns and to give a rigorous mathematical description of the pattern dynamics of aggregating region of biological individual possessing the property of chemotaxis. Here we identify a destabilization mechanism that may lead to spatially and non-homogeneous solution, and we talk about Turing instability. Here our strategy is to consider any perturbation of a solution, a steady solution, nearly and homogeneous here a steady state. And the aim of our work here is to prove that the nonlinear evolution is dominated only by the corresponding linear dynamics along here a very few growing mode and a finite number of the fastest growing mode. Okay, I give you here the conclusion. Okay, for the outline of this presentation, I introduce the principle of pattern formation, namely the Turing instabilities, and then I describe the model of Killer-Segel and how to find the instability criterion and how to link the linear instability and the linear instability and how to reach or how to compute the pattern in order to approximate the solution of the Killer-Segel system. I
I explain here very briefly the finite volume method to describe the approximation. And finally, I give you some numerical results. Okay, patterns are everywhere, and it is a celebrated questions in mathematics. Why do leopards have spots and tigers have strips? Here, in this figure, you have here zebra with stripes, and here leopard with spots, and here an aggregation of tumor cells. This is the starting point of our here work. We have asked the question if you are able to detect this aggregate region, and if you are able to detect this aggregation, we are perhaps able to treat this tumor, for example, by surgery or for example, radiotherapy. And how to do, and this tumor cells, this aggregation is viewed as a pattern. Okay, we can define the pattern. The patterns, we can define it as the solution of a reaction diffusion system, which are stable in time and stationary, non-homogeneous in space. Okay, in this case of the zebra, we consider it is a final situation, is in time, but in space, it is a non-homogeneous state. Okay, pattern formation also refers to pattern formation. We can refer it to the process of by changing a parameter, a bifurcation parameter, the homogeneous steady state loses stability in favor a stable but non-homogeneous solution. Okay, we can define it to explain, for example, this pattern. Alan Turing, in his seminal work in 1952, tries to answer to this question by considering here a model of two chemical species, U for activator and the V for inhibitor. In this reaction diffusion system, you have here F and G are the reaction term, and here we have the classical diffusion term with a diffusion coefficient here, and this diffusion coefficient should be greater than 1. And the counterintuitive idea of Turing is to consider firstly a kinetic system of chemical, which is stable. You consider the steady, stable solution. That means in the absence here of the diffusion, we suppress this diffusion term and we compute the steady state. And here, if you add the diffusion, in the presence of the diffusion, this steady, stable state becomes unstable. And it is a counter-entity because the diffusion was thought of having stability effect. If you have here a system with first order, we add the diffusion operator. In general, you have the solution is more regular. Okay, and this idea, we start by considering a stabilized reaction kinetic. We add diffusion in general to stabilize, but the result is unstable. Okay, I show you here, this is the first example from the book of Murray here. He considered Thomas system with diffusion term and with reaction term. Here we have the reaction term are here. And all parameters here, alpha, beta, gamma, etc. for the reaction term are fixed here. And the only bifurcation parameter here is gamma. And gamma represents a surface scale of the coat. Okay. Of the code here. For gamma very small here, 0.1, we have here no pattern. And when gamma increase, we find here a different pattern of the code animal. Okay, now I turn to, I switch now to the model of Kahn-Hilliard, and I explain how to find this instability. Okay, a typical model describing chemotaxi is a Kahn-Hilliard system. I show you in this video because I like this video. I don't know. Escape. Okay, escape and this one. Okay, I start from here. And okay, to illustrate here the mechanism of chemotaxi here, you have here a pipette struck by a chemical species, and this organism here detect the concentration and next modify its displacement according here to the high concentration of chemical. Oh, okay, and now I do PDF, Control L. Okay. Okay, the Kahn-Hilliard system, we have the cell equation, the cell density equation. We have the two terms here, the diffusion term, where A is the density of the cell mobility. And next, we have here the chemotaxis term. Here, chi is the response of here. Chi here is a function which depends on U. It is we call it the chemotactic sensitivity. It's translate here the response of cell towards the chemoattractant. And here V is the concentration of the chemoattractant, and it is a simple diffusion equation. The reaction term here are very simple. We have alpha is the rate of the production of chemical in the presence of the tumor, and beta is the death of the chemoattractant. Here we are interested in the degenerate Kahn-Hilliard system. This model, this system models the volume filling effect. It means that the cells here cannot move into region that are already filled by other cells. In mathematical point of view, we suppose here, we impose that the mobility and the chemotactic sensitivity function vanish at U equal 1. It is the density maximal, it's a normalized density maximal, and also U vanish at 0 and 1. Okay, it's not the aim here of the paper, but there exists a unique solution, global weak solution for this system, and the unicity here is proven under this assumption linking the chemotactic sensitivity and the mobility of the cells. Okay, now I describe the criterion of the instability of this system. Firstly, we consider, we use the same method of stirring. Firstly, we start by the homogeneous steady state for the system of Kahn-Hilliard here. In the absence of the diffusion and the attraction term here. Here the system is very simple. The reaction term here are linear, and the steady state is alpha U bar equal beta U V bar. It's corresponding as this term, reaction term are equal 0. And U bar, it's a real number between 0 and 1. And this steady state are linearly stable. And now here our target is to study the nonlinear evolution of the Keller-Segal system, but around this steady state. For that, we denote by here little u and little v the perturbation around the homogeneous steady state. It is a difference here. U, the capital U, capital V are the solution of the initial Keller-Segal system, and the little u, little v are the perturbation. Okay, the nonlinear evolution. Okay, we write here the Keller-Segal system in terms of this perturbation u and v, and we replace it in this system 1 and the system 2 of the Keller-Segal are equivalent. In order to study the linear stability of the system, now here we add and we subtract the linearization of the Keller system around the steady state. For that, we add here d bar. It is the diffusion term, but for the linearized system. Okay, we write in here. It's depend in the diffusion coefficient d and the steady state. We add this term and we subtract it. We found here in red the linear operator, and the rest here is the nonlinear operator. Okay, and D is exactly the diffusion for the initial system. Now we are interested here with the linearized Keller system. We denote here to distinguish with the two solutions for the nonlinear system and linearized system by WL, here united UL and VL, and it's written here in this form, okay, because A and chi here depend on U bar, which I can stand. And now to simplify the linear stability and stability for this system, we consider here omega be a box with a length pi. And we denote by Q is a vector of the vector of wave number. And EQ here is a product of the cosine, is the eigenfunction of the operator, the Laplacian operator. AQ is the Hilbert basis in L2. And next we look for a normal mode for the linear Keller system. We denote by here in the normal mode here, R in the form WL is the exponential of lambda by T multiplied by the eigenfunction, and here we have R is a vector. We plugging here the equation or the form of the linearized system into the equation 4. We find here that lambda are the eigenvalue of this matrix, which depend for the norm of the vector of wave number and the steady state, and here we have also the reaction term. Okay, lambda should be the eigenvalue of this matrix. For the linear instability, here we require that the real number of the real value of the eigenvalue should be positive for some value of wave number. We write here the dispersion relation to find lambda. Okay, it's here. It is very simple. Okay, we compute the discriminant of this system of this polynomial. We find it's positive. The two real the two eigenvalue are real here. And this term here for the linear term is positive. Consequently, we have lambda minus is always negative. And next, to impose that one of eigenvalue is positive, the linear instability condition here required to impose here the value of the polynomial at 0. It is this function h should be negative, and it is a linear instability condition. But if you look, this function h is a polynomial in the norm of Q, and then for Q large, h, this function is positive. And consequently, we deduce that there exists only a few finite number of wave number such that this function H is negative. Okay, and this linear instability. We have here a finite number of Q for which lambda is positive. We define here the largest eigenvalue. We denote lambda max is positive, and we note by Q here the set of the vector wave Q for which the eigenvalue is the maximum of eigenvalue is reached. And here in this set we have only 2 or 3 modes for which lambda maximum is reached. And next we can we compute here explicitly the eigenvector R here. Our main result it is to link here the nonlinear the linear instability to nonlinear instability. For that here we consider under the instability criterion we consider initial perturbation here W. This initial perturbation here, write it in the basis in Q. And here our result, here we compare here the nonlinear evolution of the Cahn-Hilliard system, here W for this perturbation. It's compared only for this function. It is only the solution obtained only for the fasted growing mode. Here we have RQ plus is the eigen vector associated to lambda plus, and we consider only this perturbation. And this difference, okay, here we have mu is a gap between the maximum of the eigenvalue and the rest of the eigenvalue here. And here the norm is not the classical norm because here we treat the degenerate case. In this degenerate case, the solution U of the cell density is not regular. So we consider here this norm. It is the inverse of the radical of the Laplacian here. And V, we consider the standard L2 norm. This estimate can explain the pattern formation in the sense of if you take T large enough, we have here exponential minus mu T is very small, and next we can consider the initial perturbation is very small, and next and so the Cahn-Hilliard system here for the linear instability is compared to only the fasted growing one. Okay, so the idea of the proof. Here the solution of the chemoattractant is concentration is very regular in V because it is the diffusion equation. And here we consider test function as minus the inverse of the Laplacian by U. And for the chemoattractant function, we consider simply the function V. And we compare here the nonlinear system to the linearized one. Here we use energy estimate to compare the two solutions. And finally, we compare the nonlinear system here to the linear fasted growing mode. Because here we have explicitly the value of the eigenvalue and the eigenvector. It is in the degenerate case, but in the non-degenerate case, here we can consider the norm L2, and this result has been proven by Coe and Wang in 2010. Okay. And the proof of this theorem is based on the Duhamel principle due in this case for non-degenerate case. And the two proofs of the theorem are very, very different. Okay, I have. I give you now to compare the dynamic of the Keller-Segal system, the evolution, and the pattern. We need here to solve the Keller-Segal system. Here we choose a very, very simple method. It is on the finite volume method. I give you here in 2 slides here. We approximate the solution here in the orthogonal mesh. It is a simple mesh, and this mesh satisfies the property of the orthogonality. It means that the segment here linking the 2 center of the element is orthogonal to the interface separating the 2 triangles. If you have this property, it is simple to give a consistent approximation of the diffusion term. Here we can write here, A is a function here is degenerate. So we apply this, we write here A gradient of U is the gradient of A, and A is primitive of the mobility. And to approximate, here is a normal flux across this interval, this segment. We use only a 2-point flux approximation by considering the value of the solution here in UL minus the solution at xk and over the distance. And now for the chemotaxis term, we see this term as a convective term. To treat this one, we use classically an upward approximation. We consider here chi is a flux, and the velocity is the gradient of V. So we decentrate here the chemotactic function according to the sign of the gradient of V, the normal component of the gradient on V on each interface. Okay, you can generalize it if you want another approximation. You can consider in general numerical flux in this sense. So we use here an Euler implicit scheme in time and this finite volume in space. Okay, I give you now, I'll show you now some numerical results. For the first test, we consider here all calculations are done in this mesh. Okay, it's a part of the mesh, and we consider here a mesh with almost 14,000 triangles. Okay, we have here the delta T and delta X. We need here to capture the pattern. We need to do the analysis to write carefully the linear instability. For that here, we consider all parameters are fixes in our system, except a parameter here is the chemotactic sensitivity. And this parameter is our bifurcation parameter. Okay, we start with our system. We have the steady state here, alpha U bar equal beta V bar. And we fix here all parameter alpha, beta. For the mobility, we have the diffusion here. We fix it this one. And the only parameter here is zeta. And we want to, it is our critical value, it is zeta. So now we want to impose the linear instability to give a pattern here. And here we have a critical sensitivity zeta is obtained by vanishing system. And for this critical chemosensitivity coefficient, here we find here that no pattern formation if zeta is below this critical number, because H is positive. And pattern formation can be expected here if Xi is above this critical number. And in this region, H is negative between 0 and this point here. This point is the intersection of the graph here with the x-axis. And this point here, we denote it is a Q star. So we have a finite range of unstable wave number here, corresponding only to this zone, in this zone. And the pattern can be expected if you are in this region. If not, there is no pattern. So we draw here the distribution of the eigenvalue. We have lambda minus is always negative, and lambda plus is positive only in this region between 0 and here 50, between 0 and 50. And we find here the norm of Q max here is obtained for Q max equal 20, and we for that we obtain the lambda max. And now we compute the set of maximal here vector wave number, and here we find only 2, 2, 4, and 4, 2. It is the norm here of the vector is equal square is equal 20. And the number of unstable here wave number is 42. It's corresponding in this cross in red here in this cross red. Okay, but all instability is done for only this 2 vector. And now we consider here a perturbation of the initial of the steady state, and the magnitude of the perturbation is very small. It's 8 here 10 porous here minus 3. Okay, it's a very small. I draw here only the perturbation. Okay, for that here the scale is very small. It's the perturbation around U bar, and U bar here is 0.5. I show here only what we expect. I show here the behavior of the nonlinear system should be similar to this stationary solution, which we called here the pattern. We draw here, it's the sum here. I recall here we have two vectors, and we write here we have only the sum of two terms. EQ is given, RQ plus is given. Here we consider W plus equal I think 1. And so this solution is the pattern. And the solution here, if you want, can be computed here. We compute it with based only on the bifurcation analysis. There is no numerical simulation here. Only we draw this quantity. Okay, we have all, and we can draw this quantity. Okay, it's not necessary to solve or to orchestrate the Keller system to obtain the pattern. It is a distribution in space, and here the exponential lambda max t, it is a scale, is only a scale number. It's change here the intensity of this pattern. Okay, it's change the scale, but in space you have all times this contribution. Okay, and now I compare the evolution here in the first row here in the nonlinear evolution computed by the finite volume method for the Keller system, and in the second row I put here at each time the corresponding pattern. Okay, we see here the evolution for T equal to 2.5, the evolution in the killer system. He detect here the aggregation. And for T large enough, we find the pattern. Okay, but if you look in the second row, at T equals 0, we have the pattern. The pattern here as only is this contribution, is the sum of the two terms. We can obtain it. If you want only the location of the pattern, you can take here T equals 0 and you draw that, you have the pattern. If you want the intensity, we multiply by exponential lambda max, and we see here the scale are exactly is very close. Okay, it's the same here, but it's in view in 3D at time equal 1000, and we have here the difference between here the Keller-Segel, the nonlinear evolution with Keller-Segel and the pattern. The L2 norm is 0.02. Okay, we draw here the relative error between the Keller-Segel and the pattern here. And we show here that the two solutions are very close for a very long time. But as we say before, our estimate are validate for T large enough. But when T goes to infinity, here is the exponential lambda max T goes to infinity, and show and here the error increase. Okay, the estimate of the pattern is true for T for large time. Okay, and here we find it's about 1000. Okay, in general, it's video, but I have not. Okay. I have time, or okay. Okay, just to show you that we can consider here another parameter of bifurcation here. The death rate, okay, the death rate here. We can do the same analysis for about the linear instability. We found a critical death beta, and next here we find also the finite number of range between 0 and this point, and we draw here the distribution of the positive eigenvalue. And in this situation, we have here the set of the vector of the wave number for the maximum of the eigenvalue. We find here is 3 modes. And all dynamics are directed by these three modes. Okay, we consider here a perturbation. And here the pattern are completely different. In this situation, and okay, the first row we show the evolution of the Keller-Segel, and the second one we find here the pattern. Okay, and the pattern here it can be computed only by the linear instability study. Okay, in conclusion. It's not easy to capture the pattern if you consider a set of parameter and you simulate your Keller-Segel. In general, you have no pattern. Okay, you should initially here to prepare the initial condition to be a perturbation around the steady state. You have to also to study the linearized system to be able to determine the bifurcation parameters. Here we have a study with one parameter, but we have many parameters to be determined if you want to capture really as a parameter. But on all case here we have shown that the nonlinear evolution of the Keller-Segel system is dominated only by the corresponding linear dynamics along a finite number of fastest growing models. And thank you for attention. Thank you.
From the audience and from the okay, questions? Yeah, any question from people attending online? No? Yes?
Oui.
And then I move with it. Okay. Yeah, so so if I remember well, in the Keller Eagle, you may have a blow up if what you call the chemosensitivity is large.
Yeah.
So I was wondering if your bifurcation parameter is do you know if it's we can switch? Is it always smaller than this critical value for blow up?
For this one here?
No, I think it was for the
for
the one with the zeta. Yeah, so the zeta key is always smaller than the critical value for the blow up.
Yeah.
Yeah. Okay. Yeah.
If you have here, zeta is below where the critical number. It's not possible to have pattern. Okay.
Yeah, I was thinking maybe you can have a different pattern of blow up. No.
No, because here we treat the degenerate problem. As explained before, for that we have the mobility and the chemosensitivity function vanish at 0 and 1, and
okay.
So your solution is between 0 and 1.
Okay.
Okay. If you consider the chemotactic sensitivity function equal U only,
yeah.
It's possible to have a blow up of your solution. Okay, but it's not the same phenomenon. Okay, a blow up is not pattern. Okay?
Yeah. But I was thinking maybe you can have both things.
Yeah, we talk about instability, but it force instability.
Yeah.
Okay, because if your solution is between 0 and 1, it's not possible to obtain a blow up. It's only a perturbation, okay, of system, but your system between 0 and 1.
Right.
Okay, we talk instability, but I think perhaps we can talk about non-homogeneous steady solution. It's better to distinguish the two notions.
Questions?
Ladies first. Thank you for the talk. I just have a question on potential equivalences. So the Keller and Saad, you cannot hear?
No.
No?
No.
Arib? Okay. So you're practically concerned with a pattern formation, which is either the strips or the dotted pattern.
Yeah.
There are other methods to getting these patterns from looking at level sets or phase field, which is modeling a field with ones and zeros. So you're kind of bounded to two values only. Have you compared or looked at these models in relation to Keller and Saad?
No, I don't compare it. If you want 1 and 0, that means you have a friend on an interface, and here we have a diffusion equation, and so the solution is not possible to use this method Okay.
Other questions?
Okay, thanks. It was very nice talk. I have a question regarding the initial conditions. So you said that it must be a small perturbation of the stable state, right? So, and you said that it cannot be a little bit far enough from the stable state. So my question is, how much we have flexibility to be away from the state to generate these patterns?
I think if you have in mathematical point of view, if you have initial perturbation, a little perturbation, you can decompose it in the basis of OQ. You can consider the projection here, and here we have some parameter W minus and W plus here. This is the decomposition. You can do it, and you can choose this parameter, and because in general, if you have a steady stable, you are in rest, you are not sick here. For example, if you have your system are you have a virus, for example, okay, your system, your steady state, you are it's a little perturbation in this yours. And next, the mechanism of pattern can be okay.
And how much this will be sensitive to numerical errors, for instance?
So I don't know.
Because you know,
numerical solution.
We have numerical errors because you are numerically solving your system. So
certainly we have. I don't know. Our solution is not exact because it's an approximation. Okay.
Yeah, but I mean, how much when you start solving your system numerically, you have kind of rounding errors and something like this. So my point is this important? I mean, this can affect the pattern formation. I mean,
no, pattern formation here. In this calculation here, there is no approximation. Okay.
This is the exact formula. Exactly.
We can see that this pattern are exact.
When you compare later with these two rows, exactly here. I mean,
and here we have certainly the error of the approximation for the Keller Segel, and okay, we can add here the numerical approximation.
But
the order, I think, is order 1.
I see.
Okay, we can add the numerical approximation. No problem.
Okay, it's fine. Okay, thanks a lot.
Any other question? Just a little question.
So you speak a lot about degenerate, non-degenerate. What is the criterion? Is it the chi or what?
And this one.
The function chi?
Yeah, the function
A.
Chi. But the degeneracy here is chi.
So it degenerates the chemotaxis term.
Yeah, chemotaxis. And here in this case, we consider the two are degenerate.
Okay.
For A, you can consider one. And if you
En cours cet après-midi. Parce que je croyais à un certain moment je vais pouvoir le faire. Je suis fatigué avec la préparation de tout.
So existence and uniqueness properties are they guaranteed, or what do you
for the uniqueness? Yeah.
So are these have been done, or you have done? You have proven the solution of this. This is at least one. So
the existence and uniqueness under this condition.
Okay, you need the like Lipschitz. Okay, so
that's right here. That's something in fact is used only for the uniqueness.
With A being.
A here is a primitive of the
of the small a.
Okay, we don't see here because of this one. Okay. And A here is a primitive of the.
What techniques do you use for the proofs?
For that, we use only the energy estimate.
Energy estimates.
At a certain moment, we need to control here the difference of kind by system, and it's okay.
And this can be satisfied.
Yeah,
in practice.
Yeah, in practice, it's satisfied because you is between 0 and 1, and all time you can ensure this property.
And what you compute is a weak solution usually. Thank you.
Because A is degenerate, the best regularity is not U, but is this function. A is only natural.
Yeah, of course, it's regular. Yeah, sure.
And,
thank you. So I think we need to thank him and the clap a little bit. So I mean online. Okay. So our next speaker is Dr. Zahra Taha. Hello. Okay. From the Ecole Doctorale, Lebanese University and Université de Poitiers. And she will be speaking about existence of solution to a Cahn-Hilliard equation with proliferation term. So the floor is yours. Thank you. Nice talk.
Hello, in my PhD thesis, I'm studying the Cahn-Hilliard equation in view of biological application, in particular with tumor growth. This is an overview for the presentation. We start with a definition of a tumor. A tumor is an abnormal mass of cells in the body. It is caused by cells dividing more than normal or not dying when they should. Tumors can be classified into benign and malignant tumors. Benign tumors stays in their original place, and they are usually not problematic, while malignant tumors spread to other tissues and lymph nodes. They spread through several stages. First, the tumor is in its original place, then it's localized in the tissue, and in third step, it's spread into surrounding tissues and nearby lymph nodes, then to deeper tissues and farther away lymph nodes. And the final stage, it spreads to other part of the body, and it's called metastatic spreading. For the mathematical modeling, in 2008, Cahn and Nader proposed a model, 1D model, to model wound healing and tumor growth. This model deals with cells that move, proliferate, and interact via diffusion and cell-cell adhesions. We know that a 2D extension for this model models the clustering of malignant tumor cells. Here, U is the local density of cells, Q represent adhesion parameter, and the lambda proliferation rate. For the function F, it's for free energy, local free energy, a thermodynamical relevant function is the following logarithmic function, where theta 1 and theta 2 are constants that depend on temperature and critical temperatures. Usually such a function is approximated by regular functions. Here is an example showing the difference between logarithmic potential and the polynomial one. We are interested in Cahn-Hilliard equations with the proliferation term endowed with the Newman boundary conditions, and such a model used to model the malignant tumor growth, where U is the local density of cells. In general, it takes value between -1 and 1, where -1 represents the healthy cells and 1 for the tumor cells. We consider the following proliferation term, where lambda 1 is the death coefficient and lambda 2 is the growth ones. In this section, we are interested in regular nonlinear terms, so we consider F as a C2 functions. First, we recall the definition of weak solution, and we note that the weak solution follows the following weak formulations. We want to prove the following theorem of existence and uniqueness of weak solutions. Here are some steps of solutions. First, we construct the basis using the following isomorphism B and some spectral theorems that allow us to have eigenvectors on the WM that form a basis for H1 and L2 omega. Construction of approximated solution, we are looking for a function UM satisfying the following equations. Then we have energy estimates for the approximated problems, and finally we can pass to the limit using these energy estimates and some compactness results. For uniqueness, we consider two different solutions. Then the difference satisfy the following equations. Using some estimations and the following interpolation, we get the inequalities. Finally, using Gromwall's lemma, the uniqueness holds. For the logarithmic nonlinear term, we consider potential function F as the following logarithmic function. To proceed, we need to write F as the summation of two functions and introduce the approximated functions F1 as a C8 function. Then writing Fn as follows, we can introduce the approximated problem, and note that the approximated problem can be written as the following weak form. For this approximated problem, we note that we can prove the existence of solution using the previous section, as here Fn is regular. For the energy estimates and logarithmic function, we consider the initial function U0 less than or the average of it less than or equal 1 minus 2 delta. Then we have the following energy estimates. In this case, we can prove that the function U stays in the relevant biological interval -1, 1. Here we have, using the energy estimates above, we can prove the theorem of existence of solution for the Cahn-Hilliard equation. Note that uniqueness and further regularity are open problem for logarithmic functions. We can, in logarithmic case, we can have a global solution if we consider that the growth coefficient is less than or equal the death coefficient. We can consider a function G more generally having h of x. H of x may have biological meaning for the nutrients more. And we find that if this condition is satisfied, then the solution is global and time. For the numerical simulations, first of all, it's hard to deal with the fourth order space equations. So we write the function as a second order in space equations. And we use first of all, for the nonlinear term, we use Newton's algorithm to get linearized problem. Then one p finite element is used for space discretization, and implicit Euler for time discretizations, and we get the following equations. In the following numerical simulation, we consider omega as the rectangle 0,5 cross 0,1, and the triangulation is made by dividing the domain into rectangles and then dividing each rectangles along the same diagonals. Here is the mesh, and it's here part of the mesh to show the triangulation. Delta T is taken here at 0.001. For the regular nonlinear term, we have two examples. First, we see that in some cases we have blow up in times. If the solution stays in the relevant interval -1, 1, we see that it converges to a value. Okay, here we note that we take the initial function in the interval -1, 1, though in some cases we have blow up in time. For the logarithmic nonlinear case, we took another function, initial function u0. We note that if the conditions in the theoretical part is satisfied, then the solution stays in the interval -1, 1. Okay, here are more examples taking different functions, u0 and lambda. Same, we make sure that the theoretical condition is satisfied. And now another example to show the tumor growth numerical results. We consider omega as a circle of radius 1.2 centered at 0.5 - 0.5. And the triangulation is about 10,900 triangles. The following delta time step is taken. Here we consider the cubic functions f, and lambda 1 is 96, lambda 2 is 280. For the initial function, we consider the following. We note that the initial function here is elliptic shape centered at the origin and along the y-axis. Here is a video to show the tumor growth. We have the purple color represent the tumor cells, while the yellow ones represent the healthy cells. We see that the tumor is spreading. Now we note that the tumors during the spread, they make mass sinks. These mass sinks are because the death coefficient, since some cells during the spreading dies, so we have the mass sinks inside the. Okay, here we can't see that the tumor is spreading to other tissue because of the boundary condition we have taken at the first. Okay, we note that to have more realistic model, we can couple the Cahn-Hilliard equations with the nutrients equations that describe the nutrients movement, and considering other boundary conditions. Okay, thank you for that.
Questions? Yes, Dr. Saad.
Okay, thank you. In general, it's we show that the solution is between 0 and 1, included in 0 and 1, and here we have U is strictly positive and strictly is less than 1. How do you show that? What is the method to show that?
The solution take values between -1 and 1.
It's minus. Okay, but in your theoretical result, because okay. But 1 and okay, you include -1 and 1 or not? Because you have the logarithm of 1 minus s and 1 plus s.
This results for cubic function of
Okay.
logarithmic strictly less than 1.
Thank you. So I have 2 questions, but I think it's more or less the same. So I didn't see in your first theorem, what was the assumption of on G? And so how did you choose G in your simulation?
This function or the simulations and the simulation?
Both actually. So yeah, what is the condition of on the function G? Is not
here we don't have conditions. Only taking this for
you take G. Only this.
Yeah.
You prove only for this one. Okay.
Yeah.
I was thinking it's a general result for any function. Okay. So and then you make this. So yeah. So I can change a little bit the question. So I just wondering why the proliferation is of order 0 in terms of derivative. So I was thinking in Cahn-Hilliard, maybe it should be something like an h minus 2 function, something in order 2. I don't know. So, but when you derive the Cahn-Hilliard from the energy, so I was thinking maybe why is not a Laplacian of G of U? If you have some idea from the modeling, no?
No. Mass source.
In a way, but so my yeah, but no, what I was thinking is maybe you can generalize for any function G in a h minus 2 or something like that. Not only restricted, yeah. But maybe I'm wrong. Thank you.
Just any other questions? No?
Yes.
Yeah, online. So let's see. How do you handle it? Yes, please go ahead, Rafa.
Hey, yes, good afternoon all.
Hi, Rafa.
Zahra, I will reiterate the question of Professor Mazen Saad. In fact, what is the argument you have used to prove the separate condition that I mean you strictly different to 1 and -1, and in which case you do obtain these results for F logarithmics and polynomial or
no?
For,
for F regular, we don't have any separation property. We don't know if the solution stays between -1 and 1. That's why we can have blow up in infinite time. We didn't find any conditions to have separation property. In the logarithmic case, we can get that U stays also a local in time between -1 and 1 using Fn and some energy estimates.
Okay, this means what you show me here no, not this one. Okay,
This one.
here you have the average of UN, which
Yes.
is strictly separate because it's less than or equal to 1 minus delta for some delta positive. Does you obtain this result also at the limit for you or not?
Yes, we obtain it for the limit also.
And this is my question. What's the argument you use to get this one? Delta is independent of n here, or?
We have the derivative for this average is equal to the average of the G with some inequalities and estimations. We can pass to, we can find constant independent of n.
Okay, that you have a uniform estimate from delta.
Yes.
Okay, and this work for that G you use here, you think you can take another form of a G and the result is still true, or you don't try for?
No, I didn't try another G.
Okay, thank you.
Thank you, Rafat. Any other questions?
Jihad.
Yes, who is this?
Jihad.
Yes. Go ahead.
Yes, I have a question concerning the simulations. Can you go to that slide, please?
Last one or before?
The last one.
Okay.
Yeah.
Yeah.
Yes. Can you please discuss the conditions of these simulations? This is a 2D domain. Maybe I missed the description. So can you go over the details and restart the video so we can go through it?
First, the domain is a circle centered 0.5 minus 0.5 and radius 1.2.
Okay,
the initial tumor.
Yeah, the region in which the initial tumor is localized. What is the shape?
Elliptic mass centered at the origin and along the y-axis.
Okay, so then you proceed with the simulation. Right, and then you reach a point where you lose bilateral symmetry. Can you explain that? Right. So can you elaborate on why you lose bilateral symmetry in this context? Is this an expected behavior, and you have results on when to expect it?
Expected due to nonlinearity of the functions.
Why should nonlinearity break symmetry? Is that established instability?
I don't know.
I don't. There is no problem of stability.
I'm not hearing the audience, but that's okay. I can follow up later.
Yes, hi Jihad, I'm Ayman.
Hi Ayman, hi.
Hi. Well, what we did in this simulation, we reproduced the same simulations as many other papers have shown. And actually, we break here the symmetry because of the nonlinearity in the functions f and g. So it's expected, it was expected to have such patterns and even to have these islands of healthy cells in yellow on this video. So it was expected. And now the other point is the boundary conditions, as Zahra said, that we can modify them and take into consideration other organs that can be attained by the growth of the tumor. So now just we stick only with one tissue, one organ that has the tumor at the middle, and the nonlinearities that are involved in the functions f and g, they generate this kind of shapes.
Yeah, I'm sure they
And these
generate them.
items.
I'm trying to understand the pathway, but maybe we can follow up in person later.
Yeah, exactly. No problem.
Yeah. Okay. Thank you very much.
Thanks.
Thank you. Thank you, Zahra. Thank you.
Thank you, Ayman. Thank you. I guess we can clap for.
So to keep up with the schedule, we decided to move on to our next speaker, who's Professor Youssef Mamri from Jean Monnet University in France. And he's going to talk about modeling carcinoma activation and impact of surgery. So the floor is yours. Please help me in welcoming Professor Youssef.
Okay. Thank you. Okay, so thank you. Let me first thank the organizer of this nice meeting to invite me. Wanted to visit Lebanon for a very long time. I don't know, because maybe my ancestors are Phoenician and they visit my country very long time ago. So I was very happy to come here. So I have the difficult task to conclude the conference, and we have seen very high level of mathematics during this conference. I hope you will not be too much disappointed by mine, because actually the math are not so sophisticated, but the medical issue is very important, and the question we try to answer with the medical doctor is also something important. So I think I will reduce the first part, because we have the previous talk who already talked about cancer, and then I will present two different work we have done for the hospital. So I will explain what is a HCC and HNSCC, so it's about carcinoma, and why we switch from one cancer to another cancer, and what we. So, but before working on that, so this is a long work. So we work on that from we start working on that 2015, I think, with the hospital. So with the Professor Antoine Garniche, so he's the head of the biochemistry department in the hospital. So he's a real medical doctor. So he sees patients every day. And so with Susanna, we work a lot. So Susanna is now, so she's a biologist, but now she's an engineer in the hospital. And then you have the three next are our hands in the hospital, the one who are doing the manipulations, or because Professor Garniche is the big boss for the medicine. I'm lucky I'm the boss for the mathematical part. So we need people to work. And so we hire Anne-Sophie. So she was our PhD student. So she was PhD student between mathematics and medicine. So she has an office in the mathematical department and in the hospital. And she has the card. She can go everywhere inside the hospital, even in place you cannot go. Okay, so the cancer, I would go a bit fast on that. So, but mainly cancer is a clonal process, and as we have seen before, it is characterized by this. So this is the main figure you can see on cancer. So, but an uncontrolled migration, proliferation, and also what is also important, the resistance to the death, so the apoptosis. So this is the cell death. So all of this make a cancer. So just to and most of the cancer are detected. So inside the hospital, how they detect the cancer, it's mainly detected by the number of mutation of the cells. So just to know. So avoid to smoke because it's a good way to have cancer. So blood cancer is a very complicated problem. So you can do every modeling you want. So many different type of models. So Bible is a big book, but genome is much more complicated. So and what you see, so in most of the cancers, so with the age, the number of mutation is increasing. So the possibility to get a cancer is also increasing. So in most of the cancer, yeah, so what we see, most of the cancer mutation will precede the cancer. So just to have a look on the 3 types of cancer. Okay, so the older you, what does it mean? Is the older you are, the more mutation we find in your cell. But okay, so just interpretation. But when they call me, they're working on something else, which is the hepatocellular carcinoma cells. So this is the most common liver cancer. And the liver cancer is, okay, I put, you cannot see very well the color of the liver cancer. But liver cancer is something very different. So, and the most important thing is that you have very few mutations. So it cannot be detected by mutations. And it's also very difficult because it's always preceded by cirrhosis. So there's very few applications, so very few surgery for this because cirrhosis is very painful. So the only treatment from for many years, I will just give a word there. Okay. So there were mainly one treatment, which is sorafenib. I will explain that, which is a targeting treatment. So now there is a new one, but it's just a derivative from the first one. But don't say it too loud. Okay, so what is so they came and say, okay, we have a medicine for the liver cancer. So I will show you that it doesn't work very well. We have few mutations. How we can detect the cancer and try to prevent it. So the main thing, so here we are not looking on the tumor growth or what we have seen before. We are looking on the very beginning of the cancer, how it activates and how it will start. And so we have to look on the very beginning. So, and one target is what we call the kinase pathway. There's many pathways, so one is the pathway. So just to do a crash course on biosignaling. So you have a chemical signal which comes from outside the cell, needs to go inside the cell. So we had some talk about that. So it come through the receptors and then go inside the cell. And the one we are looking, the pathway we are looking is the one from the protein pathway. So this is what we call the phosphorylation. So how the signal is coming from the outside of the cell to the kernel of the cell. So it will catch the receptor, go inside, activate the protein. So the protein will be activated by adding what we call a phosphate. So of the standard normal protein, you will get what we call a phosphorylated protein. So you can just imagine, so this is unactivate and become activate. And then this activate protein will activate another one, will become activate, then activate another one, etc., etc. So it can be deactivate in the other way. So by adding what we call a phosphatase. So, and what is the basic pathway? So the most common one, as we teach in the medicine. So if some of you have done some class of medicine, it was teach. So I'm lucky because the professor I'm working on with is the one who is teaching that to the medical students. So after our work, he changed his way to teach that because it's not totally true what they are presenting. So, but this is how it's presented. So you have a pathway. So this is different protein. So you have the surface receptor, and so we have this list of proteins, so not so important the name. And at the end, so the very last, so what is important is the very last, the ERK protein. So actually the activate form of the protein, because it will transcript the gene. So it is very important in all the phase of the cell. So, but this process is totally normal. So it's happened every time. But in cancer, so we know that you have a mutation of the protein. So for example, for the colon cancer, in the melanoma, the RAS is mutated. For the liver cancer, we don't know. There is no mutation actually. And so what is the therapeutic target is you need to find the drugs that will turn off this pathway. So in theory, it's quite easy. So in theory, for the liver cancer, so the name of the medicine is the sorafenib. So in theory, it's a cell like that. It will cut this arrow. So if it's going in straight line, okay, if you cut the arrow, normally it stops. But if you look to the result, it's not so good. So you can see the difference with the placebo and the sorafenib. So it's a little bit better. So you increase a little bit the survival, but not so much. So and the question was, okay, why that kind of result? So, but actually the main problem for liver cancer is that the diagnosis is very late. It's always because the patient is coming from cirrhosis, and then we see that okay, actually it's not just a cirrhosis, but a liver cancer. Okay, and so what we have from the hospital, so we have three kinds of data directly from the hospital. So we have data when so this is actually the cut of tumors. So we have data when it works. Okay, so this is the first line. So what you see is what we call Western blots. And what is important is to see that the color is vanishing. Okay, so the first one. So the most important is the P-arc. So you see in the on the left, you have no more color, so it works. It is deactivated. So the color is the activation. The more it's colored, the more it's activated. The second one is very interesting because you think it works, in the beginning it works, and then it comes back. And the last one, it never works. So we have these three types of data from the hospital, and the question they come, we say, okay, can you, with your mathematics, because in that time we will say your mathematics, can you help us to say something? So to understand this pathway, and to identify and what we have done. So I think so from the other talk we have seen. So what was very important in our approach is to combine two different things. So the top-down approach. So we have the data from the hospital. So here we have a few data, but for the other one we have a big data. So from the data, we use some statistical analysis, probabilistic analysis to get variables. From these variables, we look to the biology to know what we know about that. We build a mathematical model. We get a model, we generate new data, and we do again the process, do statistics, generate new variable, improve the model, etc. So it's not a true separate approach, it's a coupling approach. Okay, so if you look in the literature, what is the full model of the pathway? If you want to describe everything in the pathway, it's a bit complicated. So if you want to describe every step from the surface to the kernel, it's a bit complicated. So I say, okay, too complicated. So there is one model that is used a lot, is this one, but still too complicated. Too much thick, but you can see the beginning, so you have the receptor, the growth receptor, and at the end you can see the ERK. So, but it's too complicated. So when I start to say, okay, let's try to do as we know nothing about that, and we focus on the main components, which are, so actually there's two kind of RAS, and the medicine is supposed to cut the arrow going from BRAF to MEC. And I say, okay, suppose we don't know anything, and we assume that you can go not only in a straight line, but everywhere. And then we have data. So not a lot of data, but we have actually only nine data, but at different time. And then we do some statistics. And from the statistics we have done, we have seen, okay, there's no error everywhere, but the model is just this one. So, okay, this is quite good in the beginning because you are RAF, you go to MEC, you go to ERK. But there's also a very important thing that you can go back from ERK to the RAF. So this kind of retroaction, or feedback, was already known for other type of cancer. For example, for the melanoma, they also noticed that you can have what we call a feedback. So the last protein will have an action on the first one. So it can be a negative feedback, so it can reduce the activity of the first, but it can be also positive feedback. It can increase the activity of the first one. But from the data, we simplify the model. So, and then you have to explain all the chemical reactions. So I will not do a class on that, but just to remind you, because I see also very young people here. So how to model a reaction? So you have, so A plus B gives C. So it's quite easy to do. So you look to the variation of the concentration, and you just say this is the production minus the degradation. Okay, and then you can translate as an OD. But in our case, we are handling a very particular kind of chemical reaction that we call an enzymatic reaction. So what is an enzymatic reaction? So you have an enzyme, a substrate. So they will first react together and create what we call a complex. And then they separate. The enzyme come back as an enzyme, and the substrate will be modified as a product. So you have three chemical reactions actually. So one, so you have the substrate plus the enzyme will give you the complex, and then you get the product plus the enzyme. So in terms of mathematics, it's not so complicated. You can translate this as a system of 4 for the E, but so you will think I'm lazy, but 4 equations is too much for me. So usually we translate as something a little bit simpler because we are not interested so much in the enzyme. So you take the substrate and you look to the product, and you can say just the product is function of the substrate. So if you do what we call a quasi-stationary assumption, you can reduce this to only one differential equation. So the 4 equation is just one equation. So a nonlinear equation now, because the production depends on the enzyme. And then you get the second one with knowing the total. So you simplify like that. But it's not finished because we have to put inside also the medicine. And this sorafenib is acting like what we call a competitive inhibitor. So it means what? So if you add the drug, now the substrate has 2 choices. You can go with the enzyme, but you can go with the inhibitors. So you have 2 ways to do that. So you should write again 4 equations for this one, or sometimes you just write like this. And at the end, your equation is something like that. So you just modify the speed of reaction by a coefficient depending on the concentration of the inhibitor. So the coefficient alpha can be positive or negative. So if it's negative, you have a negative feedback. If it's positive, you have positive feedback. Okay. So if now I write a little bit better the pathway, what is the pathway? So I have the inactivate protein, RAF. It will become activate. So what I put with a P, or sometimes I put with a star. So the first one will be activate. Now this activate 4 will activate the MEC. So MEC become PMEC. Now the PMEC will activate the ERK, which give the PERK. Okay, and then the PERK will modify the gene, but also the concentration of PR will so the concentration of RAF will depend also on the concentration of PR. So at the end, we have a full system. So you see from the what is teaching in medicine, so straight line, we go to this. So and now the professor, when he teaches, he say, okay, be careful, because not so simple. And at the end, we get this system of differential equation. You have only 4 nonlinear differential equations, but quite easy to understand if you look, for example, the last equation. So you just see, okay, the activation of this protein depends on the activate form of the previous protein. And here you see the feedback. So actually it's a negative feedback in our case. And you get this system of 4 nonlinear differential equations. So we'll not do a lot of mathematics because the goal of this work was to deliver something to the hospital. So of course you can do your mathematics. So for example, the student, she has to do some mathematics for the thesis, but it was, if you look to the behavior of the solutions, very nice. So the model will reproduce exactly what you have seen. So you have 3 types of behavior. So you can, so when it works, so you converge to the equilibrium 0. Okay, so it's 3D, but the PR will go to 0. You have an equilibrium. So the resistance is another equilibrium, so but not 0. And what was fun is the resilient term. So you can see oscillation, and at the end you converge also to a periodic solution. So it was fun to see that, but when I say to the medical doctor, maybe can we check a little bit more if it's true? But they say, oh, no. Okay. So in terms of mathematics, it's nice, you can do the math. But what is important at the end? So, okay, I have data, I build my model, and then I will run my model. So, and for that, I will generate a lot of data. So from statistical technique, you can very easily generate. So for example, we generate 21,000 million of data. So it's the equivalent of 21 million, not 21,000, actually 21 million, 21 million experiments. But it took me 30 seconds to do that. So we have the range of the parameters, and then you run it and you look what are the important parameters. Of course, when so if you never have done this kind of thing, so the farther you are from the origin, the more influenced you are. So it's also very important if when you are doing calibration of parameters. So when the drug works, it's okay. What is important is actually the place where it is supposed to work. Okay, but in the other case, it's totally different. So you have not the parameter related with this protein, and in the resistance, it's even worse. You have something. So, and what is at the end, what is important? So you see, you have okay the RAF, but you have also this one, so the E3, which is actually the desactivation of this protein. And so what we say, so this is the simulation, but I would go a little bit faster, not so interesting. And so what say the model at the end is that actually the treatment, the drug is not used, is not cutting this arrow, not at all, actually. Actually, it plays a role on this arrow here. So it is not related to the RAF, it is related to the desactivation of this protein. So, but this is what say the model. But for the medical doctor, he has to see that in the real life. So what is important is this one. So this is what they did in terms of biological cells. So what they did, so they add an inhibitor. So this is an inhibitor that will actually cut this arrow for real. And then they put the treatment. So normally the treatment should still work if it's not related with this this arrow, but actually it didn't work at all anymore. So you see in terms of, so it was important. So the next question, I would go very fast, but then we were looking at why you have the resistance. So we go to the resistance, so you need to add surface receptor. So what are the surface receptors? So in a lot of papers, you will just find the EGFR, so the growth factor receptor. But here we are in the liver, so you have two other important factors which are related to the insulin. So and actually we have a lot of receptors, and we did again statistical analysis to select only these three. But at the end, we were able to give the optimal treatment. So you can combine different treatments to give the best treatment. So in terms of mathematics, it's not so complicated. So there's some optimal control, but in terms of mathematics, it's very not complicated. But in terms of medical science, in terms of medicine, it was actually of good, or let's say a great, as a great influence actually in many places. So we were contacted by a very famous hospital in France, in the US, in China. But in France, they say, okay, this is a liver cancer. We don't care about liver cancer. Because this is what we call preventive or evitable disease. So if you have a good health, a good food, you can avoid. So they say they don't want to pay anymore for this kind of disease. So stop work on liver cancer. And also so they say, okay, I don't remember when I start. So they say, okay, work on something interesting in our point of view, which is the HNN. So this is mostly with the same group. So with the Professor Garmisch. So we just changed our workers. So now we have intern in biology, intern in medicine, and 2 interns in mathematics. So with the Institute of Fairfax. So what is the HNC? So you cannot see very well, but it's head and neck carcinoma cancer. So this is all the cancer from the face, and also so everywhere in the face. So why it was so important? So this is the 7 most common cancer. But what was important in our place is because in the Army Hospital did the very first transplant in the world in human living. So when they say you have to work on this, you have to work on this. Okay. So the first thing, okay. So we have so now we deal with the surgery department. So not anymore with the biochemistry. So with the real surgery, so they are doing surgery, and they notice, okay, so each time they do surgery, they have a lot of relapse and very aggressive. So the migration is always very fast. So they have 2 questions. Where would be the relapse and why? And so because we know that this pathway is important, okay, we say, okay, let's do the same and try to see if it works. So maybe we were too lazy because it doesn't work at all. So actually, this pathway has no influence at all for this cancer. So there's other pathway. So yeah, we talked about TMZ last time. So TMZ is another pathway, is the P53. There's another pathway which is mTOR. So this one is a little bit more related, but actually this is not related with the protein itself. It's totally related with the surgical aspect. And how we find that? So we didn't know in the beginning. So actually the medical doctor had an idea on what should be the good thing, but I had no idea. I never did some surgery. I'm not as lucky as you. So we take the data. So and for this cancer, we have a lot of data. So if you maybe you don't know the TCGR, so the cancer genome atlas. So this is a
database, you have a lot of data. So just for this cancer, so you see you have a 427 patients. So you don't have a name, but and for each of them, you have the gene. So you have the methylation and you have the protein. So now we have a set of big data, not the 9 data I have before, but much bigger. So what we did, so I say, okay, suppose I know nothing, absolutely nothing. And so you do a non-supervised learning. You let your computer work and tell me what is related with the invasion. Or PNI is the perineural invasion, angiolytic invasion. So everything is related with the invasion. And look what happened. And then it gives you data, variables. And then we do the opposite. We take the result and we ask him, now with the supervised learning, with this data, can you find again this invasion? So it was quite nice, actually. You have more than, I think, 92% of recognition. So it was very nice. But at the end, from the whole list of genes, we noticed that only 34 were involved in this process. So, and then the question, what are these 24? Because if you read the name, you cannot. But there is a tool. So this is also why it's important to work together, because as a mathematician, I cannot, okay, I have a list of genes, but I don't know what it is. But fortunately, the people in the hospital, they know that, okay, you have a website, so you put the list of your gene, and it will explain you what is your genes. So it gives you this kind of result. And so you see the main thing is light blue is related with the cellular process itself. So, but if you have a look at the end, so from this 34 gene, actually, there's only 19 because some are the same, have the same thing. So just the name is different, but they do the same. And from the 19 we get, the medical doctors say, okay, we don't need the rest. Just keep the 7. These 7 are the ones we are interested in. So you see all the process. So from the data, we do some mathematics. We go back to the medicine, go back to mathematics, go back to the medicine. At the end, the final word is the medical doctor. So because from the 19, some cannot be a measure, so they don't need. So you need something at the end that you can measure. So what are these genes? So if you look on the list, so they are all related with the coagulation. So what does it mean? It means it's just the fact that when they cut the skin, there's blood and there's coagulation. So it's not related directly to so it's related actually with the microenvironment of the tumor, but it's related with the fact that they did some surgery. So the surgery is something very important. So it's not related only with the coagulation, but also with the fibrinolysis. So the fibrinolysis is the inverse process. So you coagulate, you aggregate, and fibrinolysis is the disaggregation. So this is what we call the coagulum. I don't know what time I have, just to. Okay, there's nobody else after me, so it's okay. And so the question, okay, so we have this lot of genes. At the end, we have only 7. And now it's not enough to explain what happened. So this is still a work in progress. So we just published the paper quite recently. So as I say, okay, the machine learning will tell you, okay, these are important, but why they are important? And the medical doctor we are working with, they want to know why it's important. So we need to develop the model. So model of coagulation, there's a lot of model of coagulation. So just to show you, or maybe next slide is not so nice. Okay. So there's many 4 processes in the coagulation. So actually there's mainly 2 processes. The one is the coagulation and the other one the fibrinolysis, which is the disaggregation. But it's described in 4 steps. So the first, you have the tissue factor, will increase what we call the thrombin, will increase the fibrin, that will increase the plasmid, and the plasmid, when the plasmid is big, it will cut the monomers, the polymers to Gmers, because at the end, so it cuts so you have coagulation. I will explain just after. So the monomers will aggregate, so it creates the polymers, and then it cuts the polymers, but at the end, you don't have necessarily one molecule. You have a polymer of the cell, so we call it D-dimer, and then you continue this process. So, for example, if you need to have a good explanation on the model, so you have this thesis. So this is also from Professor Volpert, PhD student. But we wanted to do a little bit more. So because we want to see the aggregates. So why we want to see the aggregates is because so it's still in progress, but we are planning to buy a very good MRI so we can have a very precise shape of the aggregate. But the principle is quite easy. You just say, okay, what is a particle of size I plus G? So it's a particle of size I plus a particle of size G. It's very complex. But the thing is here, so is that the aggregation depends on the fibrinogen, and the disaggregation depends on the plasmid. So at the end, you have a system. So I don't know if you are familiar with the coagulation fragmentation system of equations, or Smolakowski equation. So at the end, you have a system of infinite equation. So this is the ODE, but the number of ODEs is infinite. It's theory in terms of mathematics. So, but you have a system like that. So nonlinear system. So, but mainly what is say, okay, particles of size 1 are created from the fibrinogen. So you have a natural degradation. And then you have part of the cells of size 1 that are going, putting together with another particle. And you have the particles who are coming back from the disaggregation. So you have a particle of size 10, you can say during the disaggregation, maybe it will be 5 plus 5, but it can be 9 plus 1, and then you recover the 1. So you have to do all the possibilities. So you have this system, nonlinear system, which is too complicated. So nobody study. So I know few people who are studying the infinite system, but it's too complicated. So usually what we are looking is the moment. So mainly the 2 or 3 first moments. So if you look to the moment, so just this term. So here is a particular case of aggregation. So it has been discussed in this paper. So it looks okay for the blood coagulation. I'm not sure for the cancer coagulation. So if the 4I plus 1, G plus 1 is true. But it's mainly coming from the thermodynamics. But at the end, you have a system which is a little bit simpler. So if you look only the 3 first moments, so it is a nonlinear ODE, but we can do mathematics. So it's just to put at least one theorem in my so, but at the end, we have a criteria to say that, okay, so infinite time, you will have what we call a generation. And so this is very important. So generation, also in terms of mathematics, means the second moment goes to infinity. And we also have an idea of the time of generation. So what is the generation? So it means, okay, so during the process, so coagulation, fragmentation, something would stay, something unbreakable. So what is called as a gel. So a gel is exactly that. So you have coagulation, fragmentation, but sometimes there is something that is remaining. And it is a gel. And this gel is very complicated to remove in the body. You cannot do that. Okay. So it was my last slide. So for the moment, it's not totally in the end of the surgery. Actually, for the surgery, we also did something else, telling them in respect to the patient, where will be the relapse. You can do that also. But so to conclude, so what I wanted to show you is that, so I did not want to show you complicate mathematics, was not my goal, but I just wanted to show you that, okay, mathematics can be very useful for very concrete problems, because so at the end, this is used by the hospital, by the surgery, by a real medical doctor. And so what is also very important, maybe I didn't insist on that, is that, for example, for the liver cancer, they have absolutely never think about that. So for them, okay, it is cell like that, it should work like that. Okay, maybe there's some specificity for each patient, but why it's so different? And from this process, so that's why I said it was important in the medical community, because they saw very concretely that, okay, mathematics can help you, okay, do statistics and stuff, but they can help you also for very theoretical biology things. So why it doesn't work? And this approach, all of them, okay, is not so simple. So maybe even when I teach my medicine class, I have to think about that. So the first was very important in terms of medicine, and the second one is also very interesting because so we, especially the medical doctor, publish a lot of paper now to say, okay, it's not only the protein that are important, but also the surgical aspects. Okay, you have seen during the different talk that, okay, you have mainly the first we use surgery to remove, and then we use radiotherapy, chemotherapy. But sometimes we forget that, okay, when you do surgery, you open the body. So the patient is bleeding, so there's something. Okay. So, and so the other thing, what is important, so you cannot see very well here, but is actually something that can be specialized to each individual. Okay, so yes, maybe it's more general things. So we talk about that. So, but you need to maybe to understand that in France, modeling is mandatory in a clinical process now. So if you want to do a clinical test, you need to include modeling. So now, especially during the phase 2. So now we are developing so I don't know if you know about the 4P medicine. So now it's on the 5P medicine. So it's a predictive, personalized, I don't remember. But the future of the medicine is with the modeling. Okay, and thank you.
Okay. Open the floor for questions from the audience and even from Zoom. Yes.
Thank you for this very interactive talk between practice and theory. I just want to ask you, what are these moments? What do they mean? And you have
the mass.
Okay, can you just, you have 3 moments that you use?
I don't remember very well.
M0, M1, M2. So
big M0 is the mass.
Sorry?
M0 is the mass of the aggregates. And the other one, I think one is related to the energy, and the second moment, related also with the kinetics, but I don't remember exactly.
So the end product is that you have these interact with the oncologist. How does it work? I mean, in practice. So you have this system, you solve this system, and then.
Well, in practice, the only interesting thing for them is this time when the generation will occur.
When
the generation will occur. The system will occur. The only thing that I'm testing is, okay, we'll cut, make a blood process, coagulation will start when the gel will occur.
When the germ will?
When the gel will appear in the body.
I see. So, and this is the capital T.
Yeah. The capital T is the important thing for the practical point of view.
And you can determine the capital T theoretically, or
we have JIT bound actually. We have bound by Bidomain.
okay.
This is for the moment the best we can
This is what you can provide them.
Exactly. So like that, they can know, okay, so do we have to do another intervention before that, or do we need to wait, or do we need to give some treatment to increase the pulmonary age or the coagulation?
And this is what you can make as being individual. I mean, this is, you can make it personal to every case, or this is general, or I mean,
it's general,
this
but,
is,
it can be individual.
it can be individual. I mean, the coefficients, everything that would be adapted to each case.
Yeah, but the main problem is that so to get this coefficient, so we need a very precise MRI, and it's very expensive. At the moment, I don't.
Thank you.
If I may ask, because this coagulation process is very similar to something we see in physics as fission and fusion processes.
Yes.
So aggregation and coalescence and deaggregation. So we know something about this size distribution, that in the long time limit, it follows the power law. Granted that the fragmentation rate is constant.
Yeah. This is also
so if you have an intervention that is size dependent, you can kill off the power law and get to zero coagulants. So if you can make interventions that are based on size, which is what you're saying, if you have very good imaging that you can pin down the size of the coagulants, then you can do intervention. I think that's an important parameter in your equation.
Right. This is exactly. So we start like that actually.
Okay.
This is exactly what you see.
And if I may follow with the questions on, you started in this head and neck data analysis. You started with some reductions with PCAs, and then you did the clustering. Where this data reduction method tested for other things other than PCA and, let's say, topological data analysis, such as self-organizing map other than k-means?
Yeah, I present the result with the PCA because at the end, this is the one who works. But actually, I had an intern and I asked them to try everything.
Okay.
So they use a lot of different methods, and so at the end, we just keep
the meaningful values.
But yeah, maybe general remark for this. A priori, you don't know which method is the best one. You don't know where are the data, how they get the data. You just have the data. So you need to try methods. But you can also do. So there's also machine learning to ask him to itself to find the best method.
Yeah, true.
So, the best model.
Model selection, yeah.